Good afternoon, ladies and gentlemen. It's a great pleasure to have you here this afternoon, and happy Friday. I realize that I'm now probably the only thing that stands between you and your weekend, so I'll try to finish our seminar on time this afternoon. So, just for reference, you may want to, over the next hour or so, get connected to the Wi-Fi network here, because for our knowledge elicitation session later on, we will need the Wi-Fi connection. So, our topic today is knowledge elicitation and reasoning under uncertainty, and what's particularly interesting about this is that we will have no data whatsoever. That will be the big challenge of this afternoon. But before we go into the subject matter, let me introduce myself. My name is Stefan Conradi, and I'm the managing partner of Bayesian USA and of Bayesian Singapore. Now, typically, when I started my presentations, I have to kind of apologize for my background, because for most seminars, my background in the auto industry is not at all relevant. However, today, now that we're talking about an automotive topic in the most general sense, I think my background may actually be helpful. For most of my adult life, I've worked in the auto industry with different companies such as BMW Group, Mercedes-Benz, Rolls-Royce Motor Cars, Nissan, and Infiniti. And here you see some of my babies, if you will. And if you're shopping for a car right now, I do very much recommend the Rolls-Royce Ghost. That is an excellent car.
There's a special deal on it?
Yes, I could probably help you with that too. So, and later on I will come back to some of the work and some of the challenges I had in the auto industry when it comes to establishing forecasts, projecting way into the future, etc. Now that you know a little bit about me, let me introduce our company, Bayesian. Bayesian was founded in 2001 by two professors in the field of artificial intelligence, Dr. Lionel Jouff and Dr. Paul Monteanu. And they had originally developed a little piece of software for their own research purposes, but it quickly became apparent that this software was useful for many other people as well. So they formed a company called the company Bayesian, and their product they named BayesiaLab, a laboratory for Bayesian Networks, if you will. That is a desktop software that allows you to learn Bayesian networks, edit them, perform inference, analyze, optimize, simulate, etc. That remains the core product of our company, and we will see that in many different contexts today. But in fact, BayesiaLab has become part of a larger software platform. Now we have APIs, web simulators, academic editions, and many other derivatives of BayesiaLab. The one derivative or extension that we will talk about today in particular is the Bayesian Expert Knowledge Elicitation environment. That will be of the main focus today. And with the growth of our software portfolio, our customer base has grown as well. And here I just have a slide with some of the brands that are utilizing our technology. Perhaps first and foremost, I should point out Procter & Gamble. Thank you very much for joining us this afternoon. It's always great to have folks from Procter & Gamble here. We have lots of customers in the market research industry, GfK, TNS, Ipsos, Kantar, Nielsen, consulting firms like Booz Allen Hamilton, technology companies like Intel, Microsoft. I mean, you will recognize all these logos. The key point here is, of course, to brag a little bit about our large customer base, but I think it also illustrates how broad Bayesian networks are in their application, in the use cases where they are being employed. So really you see applications ranging from cancer research to marketing science to military strategy and so on. So with the growing customer base, we have also expanded our international presence. Our corporate headquarters remains in Laval, France, a little town about 150 miles west of Paris. I'm based out of our US office in Nashville, Tennessee. And for some time now, we've also had a small office in Singapore, from which we are serving the Asia Pacific market. So just a few notes about this afternoon. Of course, you should feel free to take pictures, notes, and so on. But all the slides you will see today, we will make available for download. So everything you see here, you will get either later this evening or over the weekend. Now, I will touch on many things throughout this afternoon, but on some topics we just can't get into a lot of detail. So on those issues where it kind of goes beyond the scope of the seminar this afternoon, I will reference our book that is available as a free download. You can just go to our website to get a PDF copy, or you can also get a hard copy from Amazon. Furthermore, I'd like to point out that we have started to issue microcredits for all our seminars, because there is a growing interest in the marketplace for researchers, statisticians who've had exposure to Bayesian networks or who've had some experience with it. So whatever seminar you join with us, whether it's like one of these short courses like today, or one of our more extensive 3-day seminars, you will always get these badges which you can post to your LinkedIn profile, for instance, to let the world know that you're somewhat familiar with Bayesian networks. Now, here is one pitch I would really like to make, and that is for our 3-day courses that we host regularly around the world. The next one that's coming up is next week in Boston, Massachusetts. We actually do have a few spaces still available. Then the next one will have an introductory and an advanced course in Chicago, and so on. So we literally tour the world, and I could probably not tell you many things about these courses, but I think there are much better sources for these courses in this room. I think, John, you attended at least one of these courses. Who else? Yang, did you join one of the introductory courses?
No, I didn't. I learned it myself.
You learned it yourself. All right. So John would be perhaps a great person to ask about our seminars. Perhaps he can give you sort of the inside perspective. All right. So this is our agenda today. We will start off with our substantive research question, and that is about the potential of electric vehicles. That's what we ultimately want to explore today. But we will very quickly realize that there isn't a whole lot of data that we can rely upon, because we're talking about scenarios far into the future. So we really have to reason to a large extent without data, without evidence. So that really creates this methodological question. Well, how can we properly reason, reliably, scientifically reason without any hard observations? Which raises obviously many, many questions, and we will start off addressing this step by step. We will start off by asking, well, how can we represent knowledge in general? How can we encode knowledge that we have? And to start off, I will present an overview of analytic modeling. Kind of what is the spectrum of models that we utilize in research in general, and I will try to point out where some of the buzzwords belong in this map of analytic modeling. But I will use that to introduce the Bayesian network paradigm, how that kind of relates to other types of analytic modeling, and I will introduce BayesiaLab. We'll quickly look at, well, how does it look like in practice to work with Bayesian networks in BayesiaLab. So once we have established Bayesian networks and BayesiaLab as a method for knowledge representation, we will then proceed to, well, how can we elicit knowledge out of our heads into a Bayesian network? How can we transfer our knowledge? And we'll go back in history a little bit. We'll talk about the Delphi method, which has been invented almost 60 or over 60 years ago as a way to extract expert knowledge, domain knowledge, and kind of build group consensus. But we'll also immediately see the limitations of that method, or why that really couldn't develop much further at the time with the, because, well, for one thing, it was a paper and pencil based method, and a lot of the kind of the method that should be utilized or that is helpful just didn't exist back then, such as the internet. So we will see how we can take this original Delphi method and expand on it, improve upon it, and connect it with Bayesian networks. So that is really what we're trying to do with the Bayesian expert knowledge elicitation environment. We want to take the principles of the Delphi method and take this approach to get knowledge out of your heads into a Bayesian network so we can then jointly reason about our problem domain. Now, once we have knowledge representation and knowledge elicitation under our belt, then we can go back to our case study, the potential of electric vehicles, and then kind of bring up some of the topics, the variables, the issues, the constraints that all relate to electric vehicles. So I will just briefly present some facts that represent the situation today. So we just get a common grounding in some of the variables that relate to electric vehicles and batteries and fuel consumption and so on. But of course, all these facts that I'm going to share represent today. What we're interested in is learning about, and we will be looking at the year 2025. And of course, the facts that hold today, they may no longer be relevant in the future. So for that, we will query your knowledge, your assumptions, your projections, whatever you assume, and we try to collect all of that into a Bayesian network so we can bring together the collective knowledge of this group, and so we can then jointly reason about the problem domain. So once we have this network, then we can perform inference, then we can see, well, with all our knowledge put together, now what volume projection would we reach? And then we can also figure out, well, what variables are most sensitive? What variables perhaps need more debate? What variables, or for what variables was there a big disagreement in this group? And so on. So that's the program. We will probably have 2 breaks. One perhaps somewhere around here, and another one just before we start the knowledge elicitation. But regardless of when we take breaks, please feel free to go outside to grab a donut, a coffee. So this should really be very, very informal. For that reason, I also encourage you to interrupt me at any time, raise your hand, shout out, whatever you like. I don't want this to be a 4-hour download. So we should have a good discussion here. All right, so this is our substantive question. What is the potential for electric vehicles? Now, I should start off with a quick definition, actually not just a definition, a simplification of this topic, because I want to look at electric versus gasoline vehicles, or just at the distinction between these two, even though there is a much broader spectrum of technologies. Of course, we have plug-in hybrids, there are fuel cell technologies out there. There are vehicles that are powered with natural gas and so on. But here we will make a very simple distinction: battery, electric, we'll just refer to those as electric vehicles, and vehicles that use some sort of fossil fuel, if you will. So gasoline, diesel, etc. Now, a lot is being written these days about electric vehicles. There's a lot of excitement in the marketplace. A lot of politicians are very active about it. So I was just browsing and looking for articles that talk about the issues relating to electric vehicles. And there was this web post that I found that had the headline, or has the headline, "Anxiety about electric cars misplaced," study says. And whenever somebody tells me don't worry, I do worry. I feel like there's a bit of an agenda here. So I read through the article, and the essence was, it concluded that basically 98% of our daily trips that we do could be handled with electric vehicles. So basically, said for what we typically drive, our commutes, trips to school, and so on, 98% of those could be done with electric vehicles. I thought, wow, that's a pretty bold statement. So I looked at the sources, and I found this article published last August in Nature, and it went into a lot more detail as to how they arrived at this number. Actually, the way they defined it, they came up with 87%. They said 87% of our daily trips, the energy requirement of those trips could be met with technology that is available today. Like, sounds also very optimistic. In the same journal, there was another article that specifically addressed range as a factor of a number of environmental conditions and available technologies. And it projected that really in the very near future, electric vehicles will be competitive in terms of driving range with traditional, conventional gasoline-powered vehicles. So if you read these articles, you might think, wow, electric vehicles could really go mainstream any moment now. And certainly there has been a lot of political energy behind this. For instance, in the 2011 State of the Union address, President Obama said, or made the pledge that there would be 1 million electric vehicles on US roads by 2015. Well, as it turns out, that target was missed by 80%. But if you now sort of look further, I mean, that target was missed, and more importantly, even though the projection is like we could do 90% with electric vehicles, today's market share stands around 1%. So what's the disconnect? Why do our parking lots not look like this? You know? Because I think this is clearly the vision, and when you actually, where I live in Franklin, Tennessee, I live just about a mile from the corporate headquarters of Nissan North America, where they have lots of Nissan Leafs. So actually in my neighborhood I see a lot of these setups, but we probably don't see it around here. So what's missing? Well, so what's missing from our electric bliss? When you look, if you will, in the fine print of some of these studies, there's one aspect, I wouldn't say that's hidden, but that is certainly not promoted, and that is we really need some fundamental behavioral modification to get those 90%. So kind of we could meet 90% of our daily requirements in travel if we simply took the train for long distance travel. So there are lots of conditions. And so with that this becomes a question of public policy. What initiatives, what laws should be passed, what incentives should be offered to the public in order to encourage electric vehicle purchase, etc. So now there is an example. There is Norway, and they have a very high share of new electric vehicles. I forgot the exact number, but it could be as much as 50%. Well, how do they do it? Well, they have quite a number of incentives, including that electric vehicles can use the bus lane. There are a lot of dedicated parking spots in businesses that are reserved for electric vehicles. And most importantly, the extremely high tax on new vehicles, which in Norway is, I think, about 100%, doesn't apply to electric vehicles. So it's really makes perfect financial sense for anybody to get an electric vehicle, because you get a car like 50% off compared to what you would pay for another vehicle. Anyway, so these are lots of things. Now think about, here we have a picture of a federal regulator who has many policy options, regulation options, and who clearly has the objective, well, we should have more electric vehicles on the road. And so what should we do? You know, should we reserve lanes? Should we offer free parking or tax gasoline, or perhaps prohibit gasoline-powered vehicles to go into city centers, sort of along the lines of London's congestion charter or something like that? Which obviously prompts many studies, a lot of research. A lot of research has been done, a lot of research is ongoing, all about, you know, what should we do to electrify our transportation. Now, of course, we all know, or we all wish, that all this is done to a very high level of scientific scrutiny, and we would certainly hope that all these studies and all the research is done, meets all the standards of science, and that those investigators base their conclusion on evidence. And in recent weeks, we've heard a lot about that we want science, we want evidence. There is an organization that I didn't know about that's called the Coalition for Evidence-Based Policy, and it rightfully demands that we want scientific data. And for us, it's really nothing new, because many of us live and breathe data. We work with big data, with machine learning, and so on, and we all know, well, that there is a lot of value to be gained from data. And perhaps we even have it as a bumper sticker on our car. This is what Edward Deming said quite a while ago. Actually, it is attributed to him, but it's actually not. Nobody knows whether he actually said it. But the bumper sticker goes like this: "In God we trust, all others must bring data." This one he definitely said, and that is, without data, you're just another person with an opinion. So, and we would probably all agree, yeah, totally agree. But now if we don't have any data, now what? And I don't think we have to stretch our minds very far to think of scenarios where we might not have any data, you know? I mean, there are organizations, companies like Airbus that are seriously investigating, planning, researching about the potential of flying vehicles, you know? So what's your data there? You know, we don't have any consumer data, how consumers would, how consumers would buy these, lease these, utilize these in their travels, you know? So how can we even, what data can we, when we get here? And there are countless examples in history where people, very smart people, have made very bad projections regarding emerging technologies. The president of IBM, Thomas Watson, said in 1943, "I think there's a world market for maybe 5 computers." More recently, in 1977, I can remember 1977, Ken Olsen, the founder of Digital Equipment, said there's no reason for any individual to have a computer in his home.
Well, he was actually right on that, because what made the personal computer work was VisiCalc.
Mm-hmm.
Without VisiCalc, you would not have had the personal computer, because they already had word processing workstations.
Yeah.
So when Xerox came up with the first PC and actually produced some of them, and then Apple copied some of the key features from their stuff, what really made everything work was when the guy came out with VisiCalc, didn't copyright it,
Mm-hmm.
and the spreadsheet introduced what if.
Yeah, that's interesting, but the spreadsheet was one of those breakthrough technologies for which there was certainly no data. You know, he probably correctly tracked computer sales and growth, but he had no data and no imagination to think that that could be a breakthrough software like VisiCalc. You know? So these projections have gone wrong. Now we have people, of course, who make very bold projections right now, such as Elon Musk of Tesla. He is projecting or saying about his company that they will have a 50% annual growth of sales, reaching 500,000 units vehicle sales in 2020. So obviously a very very large target. And with all this, with these extreme projections versus failures to project, I think really the best quote, the most appropriate quote is from Yogi Berra, who said, "It's tough to make predictions, especially about the future." I think that really perfectly sums it up. So what do? If we have no data, regardless of whether it's about flying cars, self-driving cars, drones, how can we be even scientific about this topic? What can we even do? Where does it leave us? How can we reason about the domain without having any tangible facts? So that's our methodological motivation. How can we reason about evidence? So we will quickly get to the only source that we can utilize, and that's what we have in our brains. You know, this is our human knowledge, our domain understanding, our assumption is all we can use. That is as good as it gets. So the question now becomes, that sounds kind of unsatisfactory because everybody is talking about data, big data, scientific approaches, and now we're saying, well, we just need to kind of work with the very soft assumptions that we have in our heads, our beliefs, our projections. But we should be realistic. Even if we don't have data, humans do have knowledge. It may be qualitative or quantitative, tacit or explicit. We know stuff about the world, and we can know things about properties and how they relate to each other. So our objective is now, how can we really work with this in a more scientific, in a more systematic way? Which brings us to knowledge representation. How can we format all these soft assumptions into something that we can treat scientifically? And speaking of spreadsheets and VisiCalc, actually for many years now, almost 40 years, really VisiCalc's Excel, Lotus 1, 2, 3, all these variants have been a major or a principal way of encoding knowledge. We have taken our understanding, our assumptions, our measurements, and often encoded them into spreadsheets. And from the auto industry, I can tell you that all the new vehicle projects that are being decided or rejected, it all more or less hinges on one gigantic spreadsheet that's linked together with many tables, and the decision is ultimately made on a single cell at the bottom that says net present value. So spreadsheets are a very, very common method of representing knowledge, and I'm telling you, spreadsheets are a very bad form of encoding knowledge. Why is that? Well, because spreadsheets force every problem and translate it or force it into arithmetic. But that's a massive simplification because many problems cannot be adequately represented with arithmetic. It's easy to see if you have a spreadsheet. If you do you can make cell C1 a function of B1 and A1, and you can enter values. One of the first problems is that as soon as you enter the formula, it becomes deterministic. So these relationships are deterministic relationships, which probably or could very well not represent reality, because we may have a probabilistic relationship. So we may have actually a lot of uncertainty in there, which these single point estimates in the cells cannot represent, because we are entering fixed values, but our measurements or our assumptions about reality may not be single value estimates. So, big problem. It's difficult to represent uncertainty in spreadsheets. And the other big issue is that spreadsheets are a one-way street. As soon as you enter a formula, you encode the direction of inference. So B1 can be the function of A1, and so you change values for A and you get new values for B, for change values for A1, get new values for B1. But what if you don't know A1, you only know B1? Then it doesn't work any longer. So in the real world, you may have an undetermined relationship. You may only observe B1 and then may wish to reason back to A1. But the spreadsheet can't do that. It's only, it's a one-way street. So much on spreadsheets, and just as a warning that we don't want to dumb down our problem merely by the choice of using this form of knowledge representation. So what else then? What else could we use? So, and I want to take a step back and think about what types of analytic modeling do we do? What is the kind of the spectrum of analytic models? And this sounds like a big task to, yes, please. Mm-hmm.
Do you consider SQL to just be a fancy spreadsheet, or is it a different beast?
Well, in a SQL database, or really any database, is just first of all, a data store.
It's not, because what I hear is that it's the lack of the rules, the programming rules. Like if you put Excel and overlaid a program or even a macro, you might get some of that, maybe not all, but some of that functionality.
You could, of course, in Excel, there are ways through add-ons to work around the lack of uncertainty.
Right.
You could kind of do simulation add-ons and things like that, and you could do the very same thing in SQL as well. But SQL, or pretty much any other database, has fixed relationships
Gotcha.
between variables, between data points.
So there's still things in SQL to put fine. I mean, to gross point it, there's still things in Bayesian Networks or BayesiaLab that can be analyzed that SQL either could not do it
Yeah.
or would not do it effectively or efficiently, or
Yes,
Okay.
yeah. So let's look at the map of analytic modeling, or let's create one. And as a starting point, I want to use a paper by Galit Shmueli. She's an Israeli researcher who now teaches in Taiwan. And a few years ago, actually in 2010, she has written a paper to explain or to predict. And in this paper, she points out how many researchers conflate the purpose of models. She says, oh, nowadays it's so easy to build predictive models, well-performing predictive models, that many scientists are misled to believe that a well-fitting model has an explanatory meaning. You know, you have highly significant parameter estimates, and therefore you think, well, if these coefficients are significant, then that they must have like a causal meaning or an explanatory meaning. But that is not correct. Conversely, she says, you may build a structurally true model, a model that really represents the data generating process, and then realize, well, it doesn't fit the data so well, it doesn't predict so well, and you may be disappointed. She says, you really need to build a model fit for purpose. If you build a predictive model, then your objective is just to achieve good performance, but essentially have to not care about what parameter estimates you have or what goes into the model. A neural network, a black box, may be the best predictive model. On the other hand, a true structural model may actually perform much worse than if you will, in an incorrect black box prediction device. So that's the key point she's making in her paper, and I would like to expand on that and introduce an axis for model purpose. It starts here on the very left with description, continuing to prediction, explanation, simulation, and finally optimization. So in the most general sense, we have association correlation on the left and causation on the right. So that's the model purpose. Now we come to the model source. And historically, models have you typically come out of theory. We have hypothesized about a problem domain, then encoded a formula, created a formula, and then perhaps taken data to estimate the parameters. But nowadays, we have so much data, we have fast computers, clever algorithms, we can generate models entirely from data. And some people may therefore think, if we just have enough data, that data will speak for itself, and we may not even need any theory any longer. But that is a major fallacy. We need to be very, very careful about that. And as we will see this afternoon, or in many other applications, we still need theory, even if we had lots of data. We need theory as soon as we want to discuss things like causality, causal inference, causal optimization. Data alone is inadequate. Anyway, let's now put these two axes together, model purpose x-axis and model source y-axis. And I'm now putting a placeholder, machine learning, here in the upper left-hand corner. And that really covers everything from neural networks to deep learning, decision trees, support vector machines, random forests. I put all of these up here. And clearly, these techniques exclusively feed on data. They don't really need any theory. We can just build models directly from data. But there is one major limitation, and that is that with models that are machine learned, we can perform prediction, but not much more. We're really limited in how we can interpret these models. A good example is what our cars can now do with like autonomous vehicles. They can understand their environment, what's around them. But one of the problems is the deep learning methods that they've built in. They can beautifully distinguish, let's say, between a lamppost, a tree, and a pedestrian. But you couldn't open up that algorithm and see, well, what makes a lamppost different from a pedestrian? You couldn't extract the characteristics and say, my car determines, this is John, this is a lamppost, this is a tree. We cannot extract that. So with machine learning alone, we really can't go into this side here of our map of analytic modeling. Now, why is that a problem? Well, whenever we want to think about reasoning, whenever we need to reason about a problem domain and try to understand how something works, how we might want to intervene in a problem domain, if we want to evaluate policies, interventions, etc., then we need to be on this side. And unfortunately, machine learning alone cannot help us here. What can bridge the gap? Well, that's human domain knowledge, theoretical knowledge. If we have that, then we can very well combine the two. I'm not dismissing the fantastic benefits that machine learning brings us, but on its own, we're really limited to prediction. If we want to go over here, then human knowledge is required. And in fact, what we're going to do today is we're exclusively relying on theoretical domain knowledge. We will actually not even use machine learning. Well, I should correct myself a little bit. I will show a very, very brief example of how we could use Bayesian networks with data, just kind of to show you the spectrum. But 95% of this afternoon will be purely about reasoning without data. So we'll stay in this channel here, down here. So that's really where Bayesian networks come in, because Bayesian networks offer us the ability to cover the entire map of analytic modeling. On the one hand, we can machine learn Bayesian networks from data, and we'll see that very briefly. But we can also use our domain knowledge and directly encode that into a network. So this will be our focus today. We'll be down here. Now, we haven't invented Bayesian networks. Rather, Bayesian networks were invented by Professor Judea Pearl, who has been teaching at UCLA since the 1970s, or actually since 1970. He's been there for quite a while. And his mission has been all these years really to mathematize causality, as he puts it. Because he recognized that algebra is quite limited in terms of what you can express in causal relationships. And so therefore he came up with a new formalism with Bayesian networks that allowed him to very clearly distinguish between association and causation in a very, very formal way. Now, Bayesian networks were kind of stuck in computer science for several decades. Only in the last 10 years or so have Bayesian networks become mainstream, and they have been adopted by researchers outside of computer science. And that's one of our objectives, because we think Bayesian networks have so many powerful properties that we think many researchers, regardless of their field of study, should utilize Bayesian networks. That's the reason why we're developing software, that's why we wrote our book, and that's why we're hosting these seminars to really show how powerful Bayesian networks are. Now, what specifically is a Bayesian network? A Bayesian network is a probabilistic graphical model. There are no formulas, there are no equations. The graph is the model. This is it, there is nothing else. There are just two components in a Bayesian network. One is a node, and the second one is an arc. These are the only two things that exist. And I would now like to illustrate what we can do with these two simple pieces in a fairly old example. Perhaps you've already heard about it. This is a story about a specialist in respiratory medicine, a lung doctor, who wants to encode his knowledge about his patients. He looks a little bit older, perhaps he is planning to retire soon, and he wants to share his knowledge with his successor. So he starts to think about his patients and what characteristics should be recorded or measured, what he might perhaps find in all the patient records. So here the first node, or the first variable of interest that he is introducing is age. And in our framework in Bayesian networks, we call variables of interest nodes. So this node name is age. This node has 3 states, 1, 2, and 3, and each state has a value under 30 years of age, between 30 and 65, and finally over 65. Additionally, there is also information about the probability of each of these states. This tells us, for instance, that 25% of the patients in this doctor's practice are under 30 years of age. 40% are between 30 and 65, and 35% are over 65. Now you may ask, well, where does this knowledge come from? It could either come directly from the doctor, he may just know this off the top of his head, or perhaps somebody goes through the patient records and counts all of them and sees the age distribution. All right, this was our first node. Now we're introducing a second node. Given that he's a lung doctor, smoking is probably a major issue. And so this new node has the name smoker, just 2 states. It's a binary variable, true and false. And once again, we have a probability distribution associated with it. So not so interesting so far, but now we're introducing an arc between those 2 nodes, which creates a probabilistic relationship between the states of the node age and the states of the node smoker. So looking at what we call a conditional probability table, we can now see, given that someone is under the age of 30, the probability of being a smoker is 69%, for instance. Now you may say, well, this isn't particularly exciting. We could easily represent this just as a spreadsheet. But it becomes more interesting once you add more nodes, more variables, and relate them to each other. So given that he's a lung doctor, we have other variables, other conditions and symptoms, such as bronchitis, dyspnea, which is shortness of breath, tuberculosis, Then we have a node that represents the result of a chest X-ray. And then finally, we have a node that stands for lung cancer. And now you have to imagine that behind every node in ARC is a little conditional probability table that tells us how the states of these nodes relate to each other. Now you may wonder, well, why would we want to represent our knowledge in this fashion? Well, what is the benefit here? So, and I'll now go through this one by one, through all the properties of Bayesian networks. Let me perhaps just close the door. I think you're setting something up outside.
I could ask a quick question.
Sure.
You might be covering it exactly next. In the age versus smoker example, what defines the direction of the arc?
Yes, in this case, the direction of the arc is defined by the doctor's domain knowledge. He's saying age causes smoking.
So that's to call it something a priori, that's put in the model. He's modeling that.
He is
saying
modeling
age
that.
Before.
Exactly. He said, and there will be many other relationships like that, such as smoking and cancer. The doctor says the former causes the latter.
Right, it's not smoking that makes you age,
Exactly.
or that.
Yeah, no, absolutely. Because very often those are kind of questions because you guys kind of ask the question, well, does it make sense age causing you to smoke? Well, ask the reverse question. If you light a cigarette, does your birth date change?
And
No,
it
and-
could
and-
be the case that there are examples where,
Bidirectional.
yeah,
Well-
like they both made,
Yeah.
sorry, yes, what
Is it possible?
In a Bayesian network, no.
Okay.
In a Bayesian network, no. A
Good.
Bayesian network is a directed acyclic graph.
Right.
And therefore we cannot have a bidirectional arc. However, if we have a relationship, sort of kind of a reciprocal
You
relationship,
create another one.
you create another one, or you create a temporal network.
Absolutely.
So in T0, A causes B. In time slice T1, B causes A. Things like that.
Right.
So that's how you would deal with the counterintuitive, like the stuff you find in Freakonomics? There's a lot of things out there that are totally counterintuitive, so your hypothesis is going to be wrong just because the nature of the problem is counterintuitive.
Well, actually, Bayesian networks are a great way to resolve some of these puzzles. Because once you take the situation, the description of the domain from like Freakonomics, if you lay it out in a Bayesian network, the resolution of the puzzle is almost instant. Like Simpson's paradox, I think, is one of the things that are mentioned in there. Very, very common paradox. With a Bayesian network, it just the answer pops right out why that is.
Okay,
No.
so this is pretty good for the counterintuitive and the paradoxical.
Absolutely, yeah. So we have one chapter in our book that just specifically deals with such paradoxes. Yes?
So can the Bayesian network also deal with unmeasured confounders? Like that was a perfect example. And it could be that the two really isn't one called age cause smoking or smoking causing age, but they may have a common
They may have a
cause.
common cause, yes.
Yes,
An
but this
unobserved.
common cause may be unmeasured. So does it, can your software handle this?
Yeah. The thing is, when you have an unmeasured confounder, then you don't have anything on it. There's no magic that can somehow make that go away. What it can help you understand is exactly what relationships you have and where unmeasured confounders could work and where they could be a problem. Because there could be certain unmeasured confounders that don't really affect the identification of your system. So there can be something, but because of what you condition on, it kind of tunes out that part of the network, so you don't have to worry about it. It makes understanding the risk of confounders, unmeasured confounders, very, very clear. It helps you define what precise assumptions you need to make or not.
So you can handle it and you can tease out if the unmeasured confounder can be part of the sufficient set.
Yes, yeah. So Bayesian networks make the identification criteria very, very obvious because you can use some very simple graphical rules to see what you need to condition on and what you must not condition on. Because sometimes we make the mistake, we just condition on everything, just like let's throw in all covariates that we have and then we hope for the best. But that can be totally counterproductive because it can actually ruin your identification and introduce new biases that you're trying to prevent. So, but we won't actually, the previous seminar was on this topic, causal identification and estimation with Bayesian network. We have one chapter in our book specifically on this topic.
But how do you handle numerical variables?
We quite simply, and you'll see how we import numerical data in a little bit, we discretize numerical data. And this way we can handle numerical and categorical variables side by side. Yes, please.
So you used a keyword there, discretized. So your model is a state model that will work on states?
Yes. A Bayesian network.
A finite state machine.
Yeah. A node has to have discrete states. And you may think, well, in that case, how can I deal with numerical variables? Actually, a very, very easy way, and the one brief example that I'm going to show you about machine learning will show you how we can discretize numerical variables and treat them as continuous, really, from a practical perspective. Now, here are some of the really interesting properties of Bayesian networks. The most interesting one is you can create a model that includes dozens, hundreds, or thousands of variables. And you do not have to distinguish between dependent and independent variables. You can all throw them in and just learn a model and find relationships. Later on, you can seek out what variables you're interested in, what you want to use as input and output, and so on. But initially, you just build a model. And as we build our model about the electric vehicle domain, we will start just piecing things together without really thinking what is input and output. Yeah? So, of course, if we used algebra, it would be different. Algebraic formula would be something like this. I would have one dependent variable, typically y, and then perhaps many independent variables, typically x. Yeah? So, a closely related property that relates to the lack of distinction between dependent and independent variables is that inference is omnidirectional. So once we have a network, we can reason from any node to any other node. We can go all directions. Of course, in algebra, that doesn't work. In algebra, like this regression here, I can set values for the x's and then only evaluate it from right to left. Then I get an estimate for y. In a Bayesian network, I could start with the y and then get estimates for the x's. So that makes it very interesting. I like this metaphor. I like to compare Bayesian networks to something mechanical, like a set of gears, because here I would argue you can start cranking here and then the motion would propagate through the gears, or I could start cranking there and then it would go the other direction. And most importantly, if I start here, I would see how the motion propagates. I would not only see the output, but also everything in between. And that's what you get in a Bayesian network. You can kind of trace the propagation of evidence. Another important property is that Bayesian networks are inherently probabilistic, which means that evidence and inference are represented as distribution. What is the benefit? Well, if we think about what we measure about the world, what we hypothesize about the world, there's always uncertainty involved. Think of forensic evidence, think of anything we measure. We virtually never have a hard observation like x is 3.57 whatever. It's usually a distribution. In a Bayesian network, we can directly work with this uncertainty. We can say something like, I believe the person I saw at the crime scene, I believe he was like a white male. But, I'm 80% confident you can express subjective beliefs. So this is really very helpful because whenever you have multiple pieces of uncertain evidence, it could be military intelligence where you have multiple sources, informants, satellite images, nothing provides perfect information. Bayesian networks allow you to combine that in the mathematically correct way. Or in like forensic science, criminal cases, Bayesian networks provide you with the correct way of dealing with all the uncertain pieces of evidence. And this is another interesting part. A Bayesian network even works if we don't have all pieces. So I can have one observation, but perhaps not another. And we'll see that in a little bit, how we can step by step update our model or update our inference with new observations. Of course, regression would be different because, or algebraic formula, because there we have to have single value inputs, get a deterministic point estimate, and we need all of them. I can't just provide one x, I really need all x's to get a y. But let's now get to the main reason why Bayesian networks were invented. This is really the most important part, and that is that Bayesian networks can encode causal direction, whereas algebra cannot. And I'm going to illustrate this with Newton's second law of motion, which you will hopefully remember from high school physics. Force equals mass times acceleration. This is how it always appears in the textbook. But actually, that's not how Newton presented the law. You all speak Latin, right? Read Latin at least. Quick show of hands. Latin, Brian, you read Latin? No. Okay. Oh. All right. I'll give you a translation. So this is what Newton wrote in Latin about the second law of motion, and actually the Latin is so simple and straightforward. You can directly interpret it even without familiarity of Latin. This is how he wrote it. He said that acceleration, mutationem motus, is proportional to v motrici impressa. So impressive, the force impresses on the acceleration. So that very clearly means this is a causal assignment. Force causes acceleration. So the equal sign that we have in this equation really is a causal assignment. But now if we take the same formula and solve it for mass equals force over acceleration, now of course, even though the equal sign looks identical, a causal interpretation is no longer possible. No? But how do we know what's what? Well, we need footnotes or commentary, or we need to go back to the original, but it's ambiguous. Bayesian networks can resolve that because in a Bayesian network I can directly encode what causes what. So Newton would have drawn an arc from force to acceleration. Now here's a caveat, and that relates to when we machine learn Bayesian networks, we cannot discover causality. So later on in this one brief example about machine learning networks, there we cannot give the arc direction a causal interpretation. Only when we have the theoretical knowledge as background, if we encode networks ourselves, then we can assign a causal meaning to the arcs. So that's a little bit tricky that we need to be aware of. So let me leave PowerPoint for a moment and go into BayesiaLab. Just switch that off and show you what this network that the doctor created looks like in practice. So here's our network. I'm not going into details right now how exactly the doctor built this network. I'm just saying he gave it to us, he passed on his knowledge to us, and now we can query that. Even without having a doctor here, we can query his reason, his logic. So let's perhaps start off with two nodes. I'll bring up the node for age, or rather I will bring up what we call a monitor. A monitor is this little rectangular bar graph that allows us to peek inside into a node. So whenever I bring up a monitor, I can see what's inside that particular node. So here is age, and we see the familiar distribution. I will now also bring up the node for cancer. This one we haven't seen before. By looking at this node, we learn that the marginal distribution of cancer is roughly 4% in this doctor's patient base. So now these monitors not only allow us to read, but we can also enter evidence. We can enter observations into the network. So I will set an observation on age. I will say, well, what if patient age is greater than 65? I'll double click on this bar here. I set this to 100%. The Bayesian network performs inference, and now I get an updated probability for cancer. Given that the age is greater than 65, the probability of cancer goes up to 8%. And you'll say, gee, I could have done that with an Excel spreadsheet and just run a pivot table or something. Well,
What does the value mean?
the value here in this case, here it would be the mean, the expected value of the distribution. Yeah. So that, because we always look there, the nodes always have distributions, and then BayesiaLab automatically computes the expected value or the mean value of that distribution. Yeah. So I'm removing the evidence again, so we can see here the mean age of all the patients is almost 50 years. Yeah. Now, even though we just performed inference along the arc direction, we will now attempt to reason backwards against the direction of the arc. I will set an observation on cancer and now get an updated probability distribution on age. So even though the arc direction goes one way, we can in fact reason or perform inference in both ways. So let me remove that again. Let me remove all. You may say, well, gee, I could have done even that by running another crosstab. Now I'm going to bring up pretty much all the nodes here. And I will repeat what I did before. I started off with setting age to greater than 65. That updates cancer, but it also updates all the other probabilities that we have here in this network.
So in the first example, the square boxes were around the nodes, but they were only around age and cancer. So that's just, if you're this age, this is the chance you have cancer, completely independent of everything else?
Yeah, I just didn't show the rest.
But they were part of the calculation?
They're always part of the calculation.
Gotcha.
So now I'm showing everything.
Gotcha.
So we can now, even though we may only be interested in age and cancer, I can see what's happening all around.
So the square box is literally just a display tool.
Yes.
The machine, the system is still working.
The network
The network is still running.
works whether I look or not, you know. And here I'm just choosing, let me show everything that's happening. So I've now set the first piece of evidence, then I may set a second piece. I'll say smoker equals true. I think we have at least one smoker here in this room, right, John? No? Oh, you quit, excellent, very good. I think John looked at this network one too many times.
Yeah.
Now smoker is true, and now we see how all the other nodes are updated, and especially cancer. So the cancer probability is now up to 16%. Now, perhaps at this point, the doctor may really say, hey, we should do a chest x-ray on you because you're like in a high-risk group. But let me also illustrate what we can do in terms of entering soft evidence. Because age greater than 65, smoker equals true, that's kind of a hard observation. But now perhaps the doctor, perhaps the patient is a recent immigrant, doesn't speak English, and therefore, cannot address all his symptoms or what ails him. So the doctor isn't entirely sure whether the patient has shortness of breath, but kind of what he gathers from what the translator tries to convey, he thinks probably yes. So the doctor is now entering a probability of dyspnea is 80%. So that's his subjective belief as to whether the patient has that symptom. So now, given that latest observation, that latest soft observation, our probability of cancer is now at 20%. So definitely time for a chest x-ray. And now, let's say this chest x-ray comes back normal. If that chest x-ray is good, then once again we have an updated probability and the risk of cancer is down to, below 0.1%. So this is excellent. Yes, please.
What is the value under the value row for the cancer in the parentheses?
Yes, and this shows you how the expected value has changed compared to the previous set of evidence. So if I now remove this latest observation, I'm kind of rolling back the evidence. Here's where we were before. The mean value of this distribution was 0.2, and now I'm setting it to X-ray to normal. And this shows me how much this distribution has changed.
So you don't report confidence interval.
Well, here in this case, the distribution, that's the confidence interval, because it is like the probability that the patient does not have cancer is 99.93. That's the degree of confidence. Yes, please.
Here you are presenting the condition distribution of x1 given x2 and x3. Sometimes I may be interested in a joint distribution of x1 and x2 given x3.
Yeah, and this is exactly, we can do any of this now.
Okay.
We can either manually, just by me clicking around, set different conditions, or we can, through simulation, try out a whole range of different values, response curves, etc. Let me just now show you, here for instance, given the risk of cancer is 0.07%, we'll probably send the patient home, take a cough drop or something. But if it comes back abnormal, the probability of cancer goes up to almost 80%. So, but perhaps that's not yet enough to do surgery, perhaps. So we can easily see how the evidence is not symmetric in terms of a normal x-ray says the patient is in the clear. Abnormal result says the risk is gone up significantly, but perhaps not enough yet to warrant a full surgery. So now the next thing is perhaps an MRI or what have you. So just wanted to show this as an illustration of how we can use Bayesian networks as an inference machine. We can take somebody else's knowledge and then work with it, evaluate it. We can set the things we know, then turn the crank and get the probabilities we don't know, get estimates for it. Bayesian networks are often mentioned in the context of artificial intelligence. Why is that? Well, Bayesian networks contain really two things. They contain a knowledge base, such as declarative and propositional knowledge, associational knowledge, and causal knowledge. So the doctor says smoking causes cancer. Bronchitis causes dyspnea. So that's encoded, and the network itself, that's our inference engine. And between a knowledge base and an inference engine, we have a type of expert system. We have a type of artificial intelligence. So, and chances are you have used that before, the WebMD symptom checker, for instance, where you can enter your symptoms, just like we did now, and then based on what you enter, you may get some requests, may get some follow-up questions, and in the end, you get an updated list of probabilities as to what you may have. So, but that's kind of the end user perspective of how to use a Bayesian network. I think this is an interesting one, or perhaps the more powerful one even. Bayesian networks are great to communicate to others. In my most recent corporate assignment, I was the head of analytics for Nissan North America, and my group had to evaluate all kinds of things, economic forecasts, evaluate government incentive programs like Cash for Clunkers. You may remember that a few years ago. And typically, we would develop regressions, formulas that we would use to try to attempt to explain the problem domain. But when you go into a boardroom with this, the executives look at you and say, gee, Stefan, we trust you, but we have no idea what you're saying here. As opposed to when you go into a meeting with a graph, then you can say, okay, here is how this works. I can turn to John and say, hey, you're the expert on these variables. Does this reflect how the world works? Is this in sync with your understanding? And then I turn to Brian. He's the environmental expert. Here are the variables. Here are regulatory issues. Does this make sense? So I find it very, very powerful for communicating with non-scientists how a domain works. So I find it a great way to get away from black box modeling. Bayesian networks are a beautiful way to share a transparent expert system where others can look inside, provide feedback, get comfortable with how the model works. I find it so much easier to convey research results when other people can really see how this works and compare the network to their own domain understanding. One quick word about why Bayesian networks are called Bayesian. Yes?
Quick question before you get too far.
Mm-hmm.
Are you saying that the web tool, the WebMD tool, is actually running a BayesiaLab?
It doesn't use BayesiaLab, but it uses Bayesian networks.
Okay, so it is a Bayesian network.
No.
Okay.
So Bayesian networks are called Bayesian because they use Bayes' rule or Bayes' theorem for inference. Now, Bayes' rule goes back to Reverend Thomas Bayes, a Presbyterian minister who lived in the first half of the 18th century in England. And beyond being a pastor of his local parish, he was a hobby mathematician. And he was thinking about how observing evidence should update our belief in a hypothesis. And he came up with what we now know as Bayes' rule that tells us how we should update our beliefs given new evidence. Interestingly, this wasn't published during his life. He died in, I think, 1761, and his theorem was finally published in 1763 by a friend of his, a certain Mr. Richard Price, who brought it to everybody's attention. Interestingly, it's interesting how sort of the history of math and the history of American independence intertwine, because this Mr. Richard Price, who published the Bayes theorem, happened to be a close friend of Benjamin Franklin and a lot of individuals who were very crucial in the formative period of the United States. So it's interesting how that history is intertwined. One more thing about Bayesian networks, and that's a frequent misconception, and that is that because Bayesian networks are called Bayesian, people think they are closely associated or perhaps the same as Bayesian statistics. And plenty of people have misgivings about Bayesian statistics and the requirement for having priors and that being subjective and so on. But in fact, Bayesian networks have more in common with frequentist statistics, because in the one example that you will see about learning from data, that approach is entirely frequentist. So the only commonality that we have here between Bayesian networks and Bayesian statistics is that the inference, how the inference is performed, that is Bayesian. So just to, yes?
I'm still not convinced why it is called Bayesian networks. The connection seems to be skin deep. I mean, you could simply call it the network model. Why Bayesian?
Well, and we asked that Judea Pearl, who named it. And he named it for the reason that the inference, the way probabilities are updated in a Bayesian network, is using Bayes' rule. That is the connection. And it's, if you will, a thin connection. Anyway, yeah.
The main theory underlying the way how they build the network structure, like which way the direction need to go. The formula is chain rule, is actually Bayesian.
See, you are talking about a joint distribution of certain number of variables.
Yeah.
You give me the network, I can write a joint distribution. I don't need a Bayesian. I can do it directly.
Yeah.
Okay? The connection is just superficial.
The way is actually they optimize the structure. They using equivalent number of samples, right? You do specify prior before you do the optimization.
There's no prior here.
I guess it's not covered here.
There's
No,
no prior.
here, no, there is no prior. And we, if you will, obtain priors by learning marginal distributions from the data. So in that sense, but that is not a prior that comes from your subjective beliefs, but that is a marginal distribution that comes from the data. But again, we're not going much into this today because we will build Bayesian networks exclusively out from our domain knowledge. So, and this is actually a good way to kind of summarize this first part. There are really two ways how to build Bayesian networks. One is we can perform knowledge discovery from data, and I'll show you in a minute a brief example, but what we will do today is really use expert knowledge. In practice, it is often a little bit of both, because on some aspects of our problem domain, we may have data. On other aspects, we may not have any data. So we may combine it. Anyway, once we have the network, then we can use it for decision support, for analytics, simulation, risk management, and so on. So with that, I suggest we take a 5-10 minute break, get some fresh coffee, grab a donut, and then let's see, let's continue at 2:30. That should give us plenty of time. I would now like to take a quick detour and talk about, well, what would we do if we had data? Just like a quick digression from our principal plan, because I know that chances are you have some data and you would use BayesiaLab in that context. So the example that I want to showcase here is from the stock market. It's financial data, more specifically, it's time series data. We are looking at 459 stocks that were traded continuously in the S&P 500 from the beginning of 2004 through the end of 2010. And this is described, by the way, in chapter 7 of our book. So there you'll have the full data set, so you can easily replicate this at home. Now, we're not looking at the price levels of all these stocks, rather we're looking at differences. We're looking at the day over day, oops, you didn't see this. You should have said something. So here we are.
Your password's wrong too, we should probably point that out.
Yeah.
Oh, really?
That is 05.
What did I write?
5.
Oh, I'm sorry.
Mathematically is correct, but.
Yeah, thank you. All right, sorry about that. So here we are, financial domain. We're looking at the stocks in the S&P 500, more specifically, all 459 stocks that were traded continuously between 2004 and 2010. And here I just have the first 16 of these stocks. You see kind of these wild swings, the day over day changes. Now the question is, how can we find structure in this data? Now, perhaps traditionally you would have done a large correlation matrix of 500 by 500 table, but I would argue that might be fairly difficult to interpret because everything is correlated with everything else. So just everything moves together, and you can do some color coding and fancy things. It's very difficult to really get the full picture of what's happening there. So what I want to show you now is how we can take this data, bring it into BayesiaLab, perform discretization, then run an unsupervised learning algorithm, and then look at what we find. And then we can see, what does it mean? Does it make any sense? Is this reasonable? How does it compare to our domain understanding? So let me leave PowerPoint and go back into BayesiaLab. And now I'm going straight to the data source. This is very simply formatted as a large table, 459 columns. The column header is the ticker symbol, and then in each row underneath we have the day over day stock price change. So this would suggest that on the first day that we observed, the Apple stock increased by 1% in its stock price. So let me proceed. BayesiaLab looks at this, sees that this is all continuous. So next step is about missing values processing, which is generally a very big topic, an important topic, because in a lot of domains we have lots of missing data. Here in financial data we're lucky we don't, but I just want to say that BayesiaLab is extremely powerful in terms of processing missing values. It makes it very easy, convenient, and robust to impute missing values on a dynamic basis. So we don't have time to go further into that, but we have an entire chapter dedicated to this topic in the book, so you may want to take a look at that. Next step is important, however. I should speak about that, and that is discretization. Because that is obviously, we have numerical data, in here continuous numerical data. Here, for instance, we have the distribution of the Apple stock. Now, if I had domain knowledge, perhaps I knew some important threshold values, I could manually introduce those here and set those as per my understanding. Here, however, I don't have domain knowledge, so I will leave this up to one of BayesiaLab's discretization algorithms. Now, if this were let's say if we were measuring water temperature, then perhaps 0 degrees Celsius and 100 degrees Celsius might be the most natural thresholds. But here I don't have any kind of natural reference points. So I will use BayesiaLab. I use one of several discretization algorithms. Here I'll use k-means 5. So BayesiaLab has now established these thresholds for the distribution of the Apple stock.
So real quick question. So you have, and sorry for the terminology, but you have this continuous data, and then you do a transform on it, right? You get the mean and you get the variance.
No, actually, I don't. I'm plotting it here just as a visualization, but I'm not capturing that
So that's
as
a histogram.
essentially, yes.
There we go.
Yeah. So I'm not. At no point are we working with any parameters.
It looked like you were transforming into the mean, and then.
Nope.
But this is a binning.
Yes.
Perfect.
Yeah. So,
Gotcha.
and now I'm going to ask BayesiaLab do that 458 more times for all the others using the same algorithm. Let's just do that. Let me run that. Shouldn't take very long. And then we will have all these individual variables represented as nodes. All right, here we are.
What kind of database did you just create?
Sumi?
What was the database you just created?
It was a simple CSV file underneath.
Oh, okay.
Yeah. And now it's represented internally in BayesiaLab.
So what's in the nodes? The parameters of the distribution?
No parameters. What the nodes contain are the actual underlying data points. The entire data time series is recorded in each of the nodes. And so that data we now want to use to learn what relationships may exist between the nodes.
So basically I could use tertiles or I could use quartiles as kind of a discretization.
You could, yeah, even though that may not be the best discretization. So, and that's,
You still have 500 nodes for the 500
yes,
columns, and then
absolutely. Now we have precisely 459 nodes here. Yeah. So one thing I'll do real quick is I will associate a dictionary so we can later on see the full company names. So, because I may not know every single of these ticker symbols what they mean. So here we now have that. So let me zoom out. Now I'll apply a learning algorithm, and there are now a number of learning algorithms to choose from. One class of learning algorithms is the supervised learning algorithms. Those I would use if I wanted to, for instance, classify a variable or predict one particular variable. Here, however, I don't have a target node. I want to discover any relationships that exist in this domain. So I'll go for the unsupervised structural learning algorithms. And here, again, I have a choice of algorithms, and I'll use the simplest and fastest, the maximum weight spanning tree. So this should be very quick. In fact, we're already done. So before I could finish my sentence, the learning algorithm has completed its task. And of course, in this format, it's impossible to decipher what's going on. So I'll apply a layout algorithm to untangle this. Perhaps do this one more until the appearance is nice. And now perhaps, since we have folks from P&G here, let's zoom in on Procter & Gamble. Here is Procter & Gamble is flashing up. Let me just...
And so then that's BayesiaLab's best guess for how Procter & Gamble is causally related to the other?
No.
Not
No,
causally
this is
related.
very, very important. It's not causal. We have now found associations. What we now see is the simplest possible model that describes this underlying data set.
And then the directions in this model relate to?
The directions here were arrived at what is the simplest possible network, what is the simplest possible structure. Because whenever we build models, that applies regardless of whether you do a regression or anything else, you want to have the best fit with the data and the simplest possible model structure. That's what we're pursuing here.
I mean, I get that mathematically,
Mhm.
but if I'm looking at this and interpreting it, I'm seeing all these arrows coming out of Procter & Gamble.
Oops.
What's the proper interpretation of those?
Well, in that case, the arc direction does not have a meaning. Don't
Okay.
fall into that trap.
Okay.
Our mind is geared towards believing that any arc is associated with causality, but here it really isn't. It is merely this represents the most compact representation that we can find with this learning algorithm.
So this is like a phylogenetic tree.
To me?
It's like a phylogenetic tree.
I've never heard that term, so I can't tell you.
It's like a family tree.
Family tree, okay.
You know, phylum,
But
phylum,
there's
kingdom,
still-
kingdom. the same.
But there, I would say there is a clear causal
Yeah,
structure.
I mean, the parents.
This just means
No, it's not
P&G,
causal.
Kimberly
No,
Clark,
there's
Colgate,
no causal.
Palo, and Force all move up and down together.
Yes, thank you. This is exactly it. This is exactly it,
So,
yes.
so if you looked up Kroger, like, I think it's what, KRG,
What's to the left?
you would see it in some type of association with P&G then.
Perhaps. Is Kroger in the S&P 500?
I think was it KRG or Kroger?
No, sorry.
It's not in there, not in KRG. Let me just finish this thought here. So, just bear with me. So, ignore the arc direction. Note what is associated. So we have Procter & Gamble is related to Clorox, is related to Colgate, is related to Kimberly-Clark. It seems like here we have a whole bunch of CPG companies close together. Perhaps that shouldn't surprise us. They sell similar products to similar consumers using similar raw materials, same distribution channels.
So then I can use distance, not hops, like number of hops as?
No, here it's merely presence versus absence of an arc. So just bear with me. Yeah.
So is it just higher degree nodes originate and lower degree nodes like destination nodes, or
No.
what is algorithm here?
Here what we have tried to find the simplest possible structure, the simplest possible network model that represents the underlying data. That's what we found here. Now this particular learning algorithm is highly restricted. For instance, it allows only one parent per child node. So therefore we have a very simple structure. But what we can read out of this, we can see what is close together. You know, you could look at these clusters here, or here it seems like we've all pharmaceutical companies. If we go down there, it seems like we have lots of food companies that are closely.
Well, this would make sense because when stocks move, they tend to move in a category.
Yes, and so we may say, gee, what did I learn? I could have told you that perhaps Kraft and
But you
Kellogg.
are seeing sort of a category here.
We're seeing a category.
So it would be not causal.
Hold on a second. What we can see here is essentially a natural clustering of variables that we think, well, gee, Coke and Pepsi, no wonder that they are together. But now remember, we just dumped raw data on a computer without any background knowledge, and we've recovered structure that seems fairly intuitive to us. So like Kimberly-Clark, Procter, Colgate, and so on. So that's what is interesting. This is why this is a knowledge discovery algorithm. We can find what is related. We can identify the most important relationships. If I were here, we probably don't learn anything new because we know that industries move together in the stock market. But had I applied this, let's say, in the Chinese stock market, or had I applied this to microarray data, I would probably find something that is new to me, and then I can ask, well, why are these things related? Why is there a connection? And then look for, is there a mechanical link? Is there a business link, a chemical relationship, a biological relationship? Then that can prompt my investigation. Or here, let's say I found a relationship, a link between Coke and Exxon. Of course, it's not there, but if there were one, that would prompt the question, well, why could that be? Is there like a common shareholdership, or what is it that causes that relationship? So I just wanted to illustrate this as a knowledge discovery algorithm, what we can find just by looking at data and representing it as a Bayesian network. Yeah.
What's on the left of P&G?
Sorry?
What's on the left of P&G coming in there?
Let's see.
Way over
UTX, United Technologies. And what's connected there?
there. That one.
Tyco. So you can now follow all of these. Look, we can look at this one. Here, perhaps this is interesting. Here we have FedEx, UPS, Southwest Airlines, Ryder System, CSX. Seems like these are transportation. These are all transportation companies. So you could now really step by step go through all of that and see, does that make sense? What is this here? Well, here this is Salesforce, Red Hat. Actually, I don't know most of these. Citrix, this is technology.
This technology is listed.
Yeah, those are all tech companies.
All tech companies.
What do we make about the center node?
Here, in this case, the center node would tell us this is the one that is most closely associated with all the nodes. That's kind of the best proxy for the entire stock market.
Even if that proxy is completely wild and just completely off base, it's the best
Yeah.
one of the data set.
Yeah.
So it's tending to follow the S&P 500 average better.
Yes,
Okay.
that would be a
Okay,
way
right
to
on.
look at it. So I want to just illustrate this, how we can, from data, find relationships that we can then interpret. And what I should also point out, this is not just a visualization, but this is actually a model that we can use to try out hypothetical scenarios. We could ask, well, what if Procter & Gamble had a good day in the stock market? What would be our expectations for some of the other variables? Yes, please.
So I think maybe a sidebar, and we can talk later, but you use the word time series and time series data, but this is not, you tapped at one of the curiosities I had.
Yes.
Is there anything, is there a way in which these networks can account for the temporal
Yes.
relations or lagging variables? Because
Absolutely.
This is a
Cross-sectional, absolutely.
contemporaneous
Yes.
relationship right now, even though you took the time series, you just
I
treated
just-
them as independent observations.
Absolutely, that's exactly what I did here.
There isn't, Bayesian has a capability of doing time
Yes,
series analysis.
so
Okay.
this would
That might be a totally separate conversation, but I was.
this would be obviously
by that
the natural next step here, that we don't just look at these contemporaneous
Okay.
relationships, but look at the lags and then how kind of the relationship of the lags look like.
This is daily you looked at, right?
This is daily, and we just looked at the contemporaneous relationships within a single day. So, but the natural question is, yeah, what about yesterday? What about the day before? And we could do that by learning a temporal Bayesian network.
And this is totally about the software and what you presented. So I have this data set, I have this BayesiaLab best guess analysis for the network. Can I then take this as the skeleton, as a substrate, and experiment with it? Like say, okay, I want to make, I don't know, put in a true or false, or just like tweak these values. and
Oh,
see.
absolutely. So I
this
could,
is interactive, it's not just a display.
absolutely. So I'll just showcase that here. Let me go in. Where's
Yeah.
Procter & Gamble again? I think it was here.
Because that to me seems the best of both worlds. You put in as much as you know, let Bayesian kind of figure out what the best guess is, and then you put your domain, and then you start iterating, just like any
So
software,
here
you start
I
iterating
could-
the program.
I could simulate like we did with the doctor's example earlier. Now, this is not the doctor's knowledge. This is the behavior of the stock market that we have now represented in this network. Now I can say, what if, let's say, Clorox has a good day in the stock market? What is the probability distribution of the other ones? Given
okay, so cool, so the network doesn't change.
the network doesn't change.
Excellent.
Our evidence changes,
That's
our
exactly-
scenarios. I could say
perfect.
Clorox
Perfect.
goes up, Kimberly-Clark goes down.
Perfect.
You know, what is now the likely distribution of Procter & Gamble?
So now I take tomorrow's actual data, create a model from it. That's a different, it'll create a different, theoretically, a
Yeah.
different network, and now I have a different-
Yeah, so you could, what would be interesting, what we did out of curiosity is learn a network pre-recession, post-recession, and then see whether the structure of the stock market has changed.
Absolutely.
Actually, it hasn't.
Well, even more for a confirmation thing. I mean, if the model's saying this is what it's gonna look like tomorrow, and then you run the same data, and the model's like, okay, that was pretty close, there you've got a good, you can accumulate data to really fine tune the model and get even more metadata on everything else.
A very good application of this is risk management, because one of the investment strategy objectives is to minimize the risk in your portfolio. And here you could interpret this as the further variables are removed from each other,
Yes.
the more independent they are. So you might want to literally invest around the periphery here to protect yourself against fluctuations.
Actually, I've seen this used more in category management where okay, I'm selling a bunch of Peter litter today, so there's gonna be a relationship to the bread, and there's gonna be a relationship in this one store to this particular type of jelly.
Yeah. Absolutely. Those are the things you can do. That's what actually much more practical application. Because nobody is trying to speculate on kitty litter and stuff like that. Whereas here you have everybody who's trying to outguess the market.
Yeah, but in this case, we feed it back into our computer ordering system, so we can stay ahead of the game.
Yeah. I think you had a
Actually,
question.
Explore is only one parent-child node. The spatial distances don't have meaning here, do they?
Here they don't, no.
Okay.
I could now apply all kinds of visualizations
Okay.
to showcase, for instance, the mutual information that exists between the nodes, the node force, the arc force. We can do all kinds of things to kind of make this much more meaningful so we can learn about the information content in this network. But that is way beyond the scope of today, because today we don't have data. This was just kind of an outlier here, just for reference. I know this is interesting, and we have a full chapter on this in the book. So,
Actually, my point is, let us take 4 variables, right? There are about 105 different network models. I want to find out which one is the best network model for the given data. I use the likelihood principle, optimize it, and pick up the best network model. It's a simple way of explaining. There are so many different techniques of finding the optimal model. I use the likelihood and I do it. And interpretation comes later.
yeah.
Once you get the model, the best model that describes the data, right? Then you go for the interpretation.
Yeah. So, we'll conclude this now. We'll have to, because we still have a lot of knowledge elicitation to do. So, how do we do knowledge elicitation? Traditionally, I mean, it's fairly straightforward. We do brainstorming, we do sticky notes, we use flip charts, we do group sessions, and thus bring out ideas, relationships, and so on. Sometimes it's as informal as this. Sometimes it's more formal in a boardroom setting with people with suits and ties, etc. But there are a number of issues that come up whenever you have a group discussion, and we don't have time to go through all these biases that could appear in such group discussions.
Are you talking about the average cognitive biases?
Yes, the
Okay.
typical cognitive biases that you have, the groupthink biases that you have, and perhaps one of the most prominent ones is that you have individuals who dominate a conversation in a group. It can either be because somebody is an alpha male, or because somebody is the most senior person in the room, or somebody who is new to the company does not dare speak up, who knows what. So we have issues about bringing out opinions, collecting opinions in a group setting. So how can we overcome that? Now, but in the 1940s and 50s, there was an attempt to address some of these issues, and the method that was developed was named Delphi method. Now, the inventors of this method were a bit unhappy about the name Delphi method, because they got stuck with it, because obviously whenever we hear Delphi, we think about the Oracle of Delphi and a priestess sitting on a tripod inhaling sulfuric fumes and then babbling some crazy stuff and sharing her visions. Obviously, that's not the Delphi method we talk about. We talk about the Delphi method that was invented by the Rand Corporation. They had the objective of extracting a reliable opinion consensus from a group of experts. And the way they did it was through repeatedly subjecting them to questionnaires and then playing back the results to them. So it was a sequence of questions, aggregating the results, presenting the results, having a discussion, and then iterating this multiple times. This is generally how it would look. And an important point in there is that when participants shared their opinions about certain quantities, that would be anonymous, so that people don't hold back out of fear that their boss might consider their opinion stupid, or you can easily imagine why somebody might be concerned about sharing their full thoughts on something. So that was the classical Delphi method, and the very first experimental application of this method was quite serious. Now, this was in the early days of the Cold War, and what Rand Corporation wanted to find out, and this was at the time a classified project, they wanted to figure out how many nuclear bombs would it take to destroy America's industrial infrastructure. That's what I wanted to figure out. Obviously, this was during the early days of the arms race, and lots of arms build-up, nuclear development capability in the Soviet Union at the time. So it was an important question for the U.S. to figure out, well, what are they going for? What might they try to achieve? So they were trying to find out how many nuclear bombs it would take, and in the first loop of this experiment, they came up, I think the range was between 5 bombs and 5,000 or something, a very, very broad spectrum. But then they shared that spectrum with a group of experts, and at the time this was done by mail and sending back and forth questionnaires, paper and pencil methods, etc. So after numerous iterations, then they narrowed down, and I think they came to a median estimate of roughly 250 bombs that would do the job. And it was interesting, I had a lady yesterday in my seminar in Detroit who years later evaluated that assessment, and then she concluded based on computer simulations that that was actually a pretty good guess. They obviously didn't have these methods available at the time, but the Delphi method actually brought them to a result that was later confirmed through other methods. So Rand Corporation concluded that really there is value to this method, even though they recognized, obviously, this is not like running an experiment, this is not a randomized trial, this is not even a proper survey. Rather, this is really just gathering subjective beliefs from experts. And even those experts may have different degrees of qualifications. So for all its limitations, it has value, and they concluded it is certainly better than throwing up your hands in despair, saying like, okay, we just don't know anything. So it's clearly a step in the right direction. Interestingly, Rand later on kind of questioned their own approach, and another researcher said in 1974, the analysis concludes that conventional Delphi is basically an unreliable and scientifically unvalidated technique in principle and probably in practice. And all the criticism that this researcher states is absolutely correct. Of course it is not like an experiment. Of course it is not like a randomized trial. But it is better than having absolutely nothing. So I think in that spirit we need to look at Delphi. That short of or without being able to run experiments, without having any data, Delphi is a useful approach.
They mentioned, demonstrate leads superior scientifically rigorous questionnaire techniques. Are there actually at that time were there some that were thought to be superior?
No. I mean, what is superior is like, oh, let's run an experiment.
Right.
Of course, yeah, gee, but certainly on that topic we can't run an experiment, So it's just like from which side are you looking at it? Yeah. So
Well, that's an interesting side point, Bill, bringing that up, 7 years later, they come up with it.
yeah. Yeah, and I don't know, perhaps there were like internal politics that were involved here. The Delphi method was, other fields of study kept using the Delphi method, but I don't think it has ever really become mainstream. I think there was a little bit of a renaissance of the idea of Delphi with some books that came out in recent years, The Wisdom of Crowds, the concept of crowdsourcing became a thing. So I think that it brought back some of these ideas that were pioneered with the Delphi method. So what we want to do now is compare the original conventional Delphi with our proposed approach. So we want to pick up on what they had intended at the time, but I think where they were limited in terms of its implementation. So on the left column, we have conventional Delphi. Here on the right, we have our proposed approach with the Bayesian expert knowledge elicitation environment. Now, back then, with the original Delphi, they were typically trying to get to single point estimates, like what is the number of nuclear weapons that it takes to destroy the US. Their principal objective was about reducing uncertainty. We're not necessarily wanting to reduce uncertainty, rather we want to capture the distributions that exist in the opinions of experts. So we want to see how much they have in common or how much they diverge. So we're looking at distributions and capturing the uncertainties. Also, back then, they were principally after getting to marginal probabilities. We, however, are looking for conditional probabilities. We'll ask, given x, then what would be the value of y? That leads us to many relationships, many dimensions, as opposed to single dimensions and single quantities. Original Delphi was mostly going after just straight to the answer. Well, how many weapons does it take, for instance? We are not trying to find a direct number. Rather, through our process, we want to build a model for reasoning, something that we can then reuse over and over again with different assumptions. And this is a key point here, whereas the original Delphi was a process that concluded and then there was a number at the end. We, by virtue of having a model, we can backtrack. So even if at the end of today we come up with a number, somebody else might take the same model tomorrow, enter different assumptions, and reuse that. So we can revisit results that we arrived at earlier. And this is something that always troubled me in the auto industry, because very often decision-making processes would conclude for certain milestones, and then everything that went into the milestone was kind of discarded, and then just the results from the milestone were carried forward. And if you realize that what led to the most recent decision was somehow flawed, you couldn't really figure out how to unwind that most recent decision, because it was just like, okay, that was made. There's no way to revisit anything that went into that decision. So I'm looking for a reversible process and one that is compatible with data. So, because if we think about a model of a problem domain, about the future, as we over time get into the future and perhaps observe and collect data of our problem domain, then we want that data to be compatible with our model and perhaps update the model or ultimately replace the model. So we can gradually replace our original beliefs with real-world data, and we can measure, well, to what extent were our beliefs compatible with what we now observe in the marketplace. So that's what we want to do. Here's a visual comparison. This is our classical Delphi method. where really knowledge elicitation and inference were one and the same. We're just trying to get straight to the answer. Our proposed approach is that we want to take things step by step. So our knowledge elicitation is still based on the Delphi method. So we iterate, we ask questions anonymously, we collect the feedback. So that is in the spirit of the original Delphi method, but we are using our technology. We are going to use BKey. But then once we have elicited this knowledge, this is what we're going to represent in a Bayesian network. We capture that and encode that in a Bayesian network using our BayesiaLab software, and then we can use that Bayesian network subsequently to perform either forecasts or inference or simulations. So we really have three separate steps: the knowledge elicitation, the knowledge representation, and then prediction and causal inference. Yes, please.
So basically with your Delphi method that you would generate a DAG and so you model, right?
Yes.
Yeah, okay.
Yes.
And would your DAG have the ability to say, okay, certain path may be not that certain than
Yeah.
the other? Okay.
Oh, absolutely. We will, as we will build a DAG, a network in the brainstorming process. We may add arcs that later on turn out to be really unimportant, because you will individually rate these relationships, and you may just conclude, or all of you may think that relationship is really weak, and we would conclude that an arc really doesn't need to be there. Yeah.
Or the initial DAG didn't have that path, but data may show there is a path.
Yes, later on when we have data, but in our case we don't have data. Yeah. So, does anybody know what that is?
Scaffolding?
Scaffolding. What's the material?
Bamboo in Asia.
Bamboo, yes. You see in Hong Kong, for instance, 50-story skyscrapers being built with this bamboo scaffolding.
Extremely strong.
Extremely strong. And I find it kind of remarkable because if you look at bamboo individually, it's things like it's kind of soft material, it's not straight, it's not like oak or something that, it's held together by strings. Every piece is a different length. I think it's actually not a bad metaphor for what we're trying to do, because what we all know about a domain, nothing may be, not a single opinion about any aspect may be perfect, correct, or appropriate, but once you put everything together, link it up, you get a remarkably robust structure that is useful for many things. That's what I think what we can do with this knowledge elicitation method. So let's get to it. Let's see what this looks like in practice. Here's the overall workflow. We will start off with brainstorming. This is where we will establish variables, figure out what plays a role in our domain, what are the causal relationships, and then in some instances we'll also have to figure out, well, what states should the nodes have. So we will do this in BayesiaLab with the facilitator. In our case, I will be the facilitator. The next step is then the knowledge elicitation, where through BKey you are being queried to assess the relationships in the network that we've defined. So you will be able to say, this is how it works. You submit your assessments, we play them back, and then we may go through this several times. And once we have all your assessments, then we will jointly review the results, and then we can simulate with this, we can optimize, we can try out different scenarios, simulate different policies. And once we feel comfortable with the model, then we can publish it. We can actually make that model available to others so they can perform their own simulations. So here, retelling the same thing as a visual. So here, this is me, the facilitator, with BayesiaLab here on my computer. We'll be all looking at this big screen, and you guys will be the experts. What's important to point out, that initial stage is purely qualitative. We'll just say, this plays a role, that plays a role, that plays a role, that's related. But how exactly will be left up to you later to assess individually. The mechanism for the elicitation is this. We will have the network, the qualitative network here on my laptop. This will go to our Bkey server in France, from where you will log in, and then through your, whether it's your iPhone or your tablet or your computer, you can then enter your assessments about the individual relationships. That's the quantitative part of the network. And this may repeat several times until we're comfortable with it. Once we have elicited everybody's knowledge, then we can jointly assess the response. We can project the network again, run simulations, optimizations, and then finally publish it, if we wish, to the wider world. So then anybody with web access can then experiment with the model. Any questions so far? Yes, please.
So the phone computer app that the subject matter experts are accessing, what's the delineation of roles between them and the facilitators in terms of, for example, is everybody creating nodes and arcs? Are just the subject matter experts just putting in the data, and is it
yes.
Yada yada.
Good point. The experts are just assessing the relationships. So you will have an interface that allows you to quantify the relationships that earlier we all established qualitatively in our brainstorming session. So you're not individually creating arcs and nodes. Rather, in the group, we'll say, this is relevant, that's relevant, but then you will determine from your perspective how strong that should be. You will see that in your interface. It's a web-based interface.
So again, thinking visually, we start off with a blank page, and then we sit around and we start saying, okay, age is a factor, smoking is a factor, and cancer is a factor. Now we've got three nodes on my display. Is that close to?
Yeah, actually, we will jointly look at this screen as we throw out these variables and come up with potential relationships.
So it is preceded. We do have a graph which is and then we iterate on that.
Exactly. Yes. That's exactly how it will work. So, good. Now that we conceptually know how this is going to work, let's now go back to our case study, and let's now discuss some of let me now share with you a little bit of some background, so we just have a common background on some of these aspects of this domain. Yesterday I was in Detroit, so we had lots of folks from GM. They obviously knew a whole lot about this problem domain. So everybody has a little bit of a common background. So perhaps this is our happy vision of the future, windmills, solar panels, we charge our cars at home, all that. What I want you to think about now is the year 2025. Seems far away, but really isn't that far in the future. It's like one car generation in the future. And just to kick off, I would like to get your gut feel. Just off the top of your head, right now, what do you think? What share of new vehicle sales will be electric? We saw earlier, currently it's 1%. What is it going to be in 2025?
Is that the right question?
I don't know. I'm just looking for
Well,
it.
the reason I was putting that up is new car sales may be directly impacted very heavily by driverless cars and by Uber, because they're predicting
Absolutely. So that's
a massive deficit in
totally. Absolutely plays a role. And that's what we discussed in a lot of detail in proper analyzing. What I just want to juxtapose is sort of your gut feel as opposed to what will our conclusion be once we take all these things into consideration. And sometimes the difference is quite dramatic. So, yes, so if
You mean electric, you mean that include hybrids or that?
No, just electric, pure battery electric vehicles. And then later on I can also share with you what the other groups in earlier sessions said on this. All done? Okay. Then I'll move forward. Let's talk now a little bit about the technology background. And one thing that we need to do right up front is we need to switch into thinking metric. I know for all the Americans in the room, this is tough. For those of us who are from Europe or from Asia, we may be much more comfortable thinking in metric terms. So we'll have to talk about kilowatt hours, kilometers, liters, and so on. So just as a background, because we need to ultimately find a common scale on some of the measures, because electricity, the energy storage of electricity is typically expressed in kilowatt hours. So we have to kind of link miles per gallon or the energy content of gasoline back into a common unit with electricity. So that's the reason why we need to think metric here. Just a quick note on fuel economy, and I'm now touching on just a number of topics that I believe will all relate to electric vehicles. And whenever we talk about electric vehicles, I think it is fair to say we'll talk about fuel economy. The way currently fuel economy is typically measured here in the US is with the EPA test cycles. The EPA, those are the numbers you see on the window stickers of new vehicles. And the EPA measures or establishes the fuel economy by putting vehicles on a dynamometer. I find it a very difficult word to say, and subjecting them to a very specific test cycle. There is a city cycle of very specific length with a very specific driving profile. There is a highway profile, and then the EPA combined fuel economy number is a weighted average of city versus highway fuel economy. So let's take a look how the cars that are currently in the market, where they range on the spectrum of fuel economy. So there's actually a scale that has two rows. The bottom one is perhaps the familiar scale. This is the combined MPG number. The top one, that is the same value converted into kilowatt hours per 100 kilometers. So that's the scale we will ultimately use as we proceed in our analysis. So at the bottom end of the spectrum, with a very good fuel economy, high energy efficiency, we have 3 electric vehicles. Here is the BMW i3, the Nissan Leaf, and the Tesla. So they have energy efficiency of roughly 15 to 25 kilowatt hours per 100 kilometers. Then going further up, here we have the Toyota Prius, around 40 kilowatt hours per 100 kilometers. Here we have 2 diesel vehicles, which may unfortunately disappear from the US market soon. The Jetta diesel and the BMW 320i diesel. Further up, mainstream family sedans, around 75 to 85 or 75 to 80 kilowatt hours per 100 kilometers. Then here we have larger vehicles such as minivans and pickup trucks, 95 to 100. Here is the Cadillac Escalade 110, Chevy Corvette as an example of a sports car. And then here we have the Infiniti QX80 with 140 kilowatt hours per 100 kilometers. And then finally, the Rolls-Royce Phantom. And you may rightfully ask, well, who builds such gas guzzlers these days? I mean, who are the people who are behind such inefficient vehicles? And I have to admit, I am one of them, because I was product manager of the Rolls-Royce Phantom between 2001 and 2004, and I was product manager of this Infiniti vehicle from, 2006 through 2008. So guilty as charged.
What, no Ferrari up there?
No Ferrari. They would be up here as well. You know, there are several others that are right up there in their lack of fuel economy. So now you may wonder, well, why is there such a big spectrum? You know, actually the Tesla that's a pretty hefty car, and the mass, the weight of the Tesla is actually remarkably close to the mass of the Rolls-Royce Phantom. So how is this even possible? Aren't they all subject to the same laws of physics? You know, they have mass, they have acceleration, they have air resistance. How could they differ by a factor of 10 or 50 or 5 or 10? Why is there such a difference? Well, one explanation why electric vehicles seem to be so much more efficient than gasoline-powered vehicles is this. The combustion engine actually isn't terribly efficient. The problem is the chemical energy that is stored in gasoline, only a relatively small percentage actually gets converted into mechanical energy that arrives at the wheels. A lot of the energy gets wasted in terms of noise, heat, vibration, and so is lost. So now with an electric motor, that seems to look a lot more attractive because of the electrical energy that's stored in the battery. A very large percentage gets converted into mechanical energy. And once the car is moving, when you brake, you can actually recuperate some of your mechanical energy back into electrical energy. Your electric motor can work as a generator when you brake your electric vehicle. So, and you may say, wow, this is fantastic. This is, shouldn't we just use this? Well, it has merely shifted the inefficiency, because chances are that the energy that goes into your vehicle's battery was originally generated either by coal or natural gas. So there you had the inefficiency further upstream. So if you look at the whole thing together, they're actually remarkably comparable. But if you just compare what's between your energy storage and the wheels, then the electric vehicle looks much more efficient. Anyway, just for background, just to provide context for why are these numbers so different. Another thing that is important to consider is energy density. And let me ask you a question in this regard. Here we have a typical automotive battery. You probably have one like that in your car, pretty heavy. Some of you may struggle to lift it out. You know, it's really a pretty big thing. Now, and this typical battery contains approximately 0.9 kilowatt hours of energy. How much gasoline would we require to store the same amount of energy? What's your guess? How much gas, what would be the equivalent of this energy in gasoline? Teaspoon? Anything else?
I think you're talking about 2 quarts, aren't you?
2 quarts? Okay. Any other opinions? Anybody else?
A quarter of a gallon.
Huh?
A quarter of a gallon.
Quarter of a gallon?
4 ounces.
4 ounces? Okay, here's the answer. Yesterday we had a much broader spectrum. Yesterday we had everything from a teaspoon to 100 gallons. So the answer is 6 tablespoons. So about half of what is left in this bottle. And that is obviously quite a difference. I mean, this one we can barely lift. That one is, yeah, about this much or so, which tells us that the energy density of gasoline is about 100 times greater than the energy density of batteries, which means that the vehicle that currently has the greatest energy capacity in the market, the Tesla P100D, that has a storage capacity of 100 kilowatt hours, that's roughly equivalent to 3 gallons of gas. Well, we also need to bear in mind that the battery pack of a P100D roughly costs $25,000. So it's hugely expensive as opposed to the gas tank in your car. You know, it perhaps costs the manufacturer $50, you know, the actual gasoline container that's in your car. Could be even, perhaps cost less. So there's a huge discrepancy in the storage cost of electricity versus the storage cost of gasoline. Now, I'd also like to share with you the energy capacities of different vehicles in the market. Again, this is recorded as kilowatt hours. Here at the bottom end, here we have the Smart 4.2. That has a storage capacity of 15 kilowatt hours. That is roughly half a gallon of gas. And here, Nissan Leaf, BMW i3, that's roughly a gallon of gas in gasoline equivalent. Chevy Bolt, 60 kilowatt hours. Finally here, Tesla, which seems like a lot, but if you compare it to the energy capacity of conventional powertrains, you know, even a mainstream sedan, something like a Corolla or Camry, they have an energy capacity of 500 kilowatt hours or greater. So that's one of the big issues that perhaps explains why it's currently difficult to achieve a greater market share. Closely related to the capacity is also, and I already mentioned it, the storage cost. Right now it costs about $200 to store, to store 1 kilowatt hour of energy in a battery costs roughly $200. So, but who knows what it will cost in 5 years, in 10 years? These assumptions you have to think about. And nobody really knows how it continues. I mean, I'm sure companies who are active in this field, they have projections, but we don't. There is no hard data. That is not yet in the market. So here we need to make assumptions. The following is also something we need to make an assumption about. Let me ask you this. How much do you pay for electricity? What do you pay for 1 kilowatt hour of electricity? 10 cents? Yeah, very good. 10-year average has been 10 cents. Interesting, in yesterday's group, people had no idea, or they were all over the place in terms of what the cost is. So that's electricity. How about if you purchase the same amount of energy in the form of gas? Would that cost more or less? What do you think? More? Less? Any other opinions?
What kind of averaging are you using? Because gas has been as high, almost $4 a gallon, and as low as $2 a gallon over different periods in that time.
So here I'm going to share with you the 24-year average across the country, and that is 6 cents. So that's what it has been. So I think for our discussion, it will be important to understand, well, what will it be in the future? You know, What?
Is that per raw kilowatt hour of energy density unit, or is that per efficiency in the vehicle?
Just how you purchase that energy. Yeah.
You can't get that much out of it.
Potential to do.
Well, yeah, of course, depending on whether you get the electricity, this is kind of the raw energy you acquire, what you pay for.
Yeah.
But then the efficiency is obviously different. Yeah. It depends on whether you put the energy, and it will be different on different types of vehicles. Yeah. So, all right, these are just a number of random facts, and I think they kind of sort of prepare us for this discussion. So we will now get to our knowledge elicitation exercise, this particular part. We'll have to brainstorm about the things that apply to this problem domain. And I want to provide you with a little bit of guidance, kind of to steer the model building process, just because we don't have a whole lot of time for this exercise, so I want to provide kind of an overall outline for the model. What I'm going to say is that I think one of the premises we should make is that consumers respond to incentives. I think that's fairly easy to defend. Also, what we should think about is the long-term demand, if you will, the unaided demand, before the government comes up with a new scheme for incentivizing, or before we penalize gasoline or prevent vehicles from entering city centers, and so on. So I just want to think about basically what it is like today, and thinking about how the external conditions evolve into the future, but without any artificial interventions. This is how I'd like to look at it. I want to look at a set of variables that describe the powertrain type. There are really only two in our simplified scenario, electric versus gasoline. But these powertrains have a number of very important characteristics in which they differ. We already talked about it. We talked about gasoline powertrains have a typically much greater energy capacity, but less of an efficiency, and so on. So we want to capture that in a set of variables that relate to the powertrain. Then I would like to explore variables that describe external conditions. That may include, how people travel, where they travel, how they drive, all that kind of stuff, what kind of vehicles they have. And then I'm saying these external conditions, they will interact with the characteristics of the powertrain. And one thing that will come out of it is cost, because I can have a set of requirements, and depending on which powertrain I choose, it costs me more or less, because we know the efficiency can be very different, and therefore if I travel 100 miles in a gasoline-powered vehicle, that may cost me more than traveling the same distance in an electric vehicle. So there is an interaction between the external conditions and the powertrain type. But there can also be constraints because of the limited energy capacity. An electric vehicle may not get me home tonight. I'm planning to drive to Nashville tonight, so I may not, if I had an electric vehicle, I might not be able to travel that distance. So that would not be an option. It might be the most economical if the vehicle could take me that far, but I can't choose that. I can't minimize my cost, because then I wouldn't get where I wanted to go. So this is how I'd like to set up the model, that we look at external conditions, the characteristics of the powertrain, constraints, and then cost.
What about incentives?
Incentives, they would go here into the cost. Yeah, but I would like to defer incentives to a later point, because that would be a policy option. I would like to look at it just from a baseline, what would, if we now look into the future, as we look at the evolution of technologies, where would we get to? And then establish what would be the natural mix of electric versus gasoline-powered vehicles, and then say, well, is that enough? You know, we need to meet, let's say, the Paris Treaty, what have you, and therefore we want to raise that, and therefore we need to do incentives. And then perhaps through incentives, we could increase the mix of electric powertrains. But I want to look for the baseline first. So we need to think about what variables play into this, how these variables relate to each other. Early on, we need to simplify, because I think we'll very quickly find like one thing leads to another, and we'll look at many, many, many details which we'll quickly have to discard to even make inference possible. Also, one more thing, let's only think about passenger vehicles, so cars and light trucks. So we're not looking at delivery vans, at semi-trucks or any of that. We're just looking at the cars that probably we would normally drive. And just to avoid any disappointment, this exercise we will just do in about a half an hour, which if we did it properly would probably take 3 days. We do offer knowledge elicitation workshops on a commercial basis, and we conduct them on a regular basis with different clients on different topics. I know we've conducted some with P&G in the past. So this will really be just a proof of concept exercise, and I don't think we'll have the final answer on this topic. So, questions so far? All right, let me leave PowerPoint. And go into BayesiaLab again. And I'm just looking at the clock. Perhaps what we should do, it's now 3:45. I think this would be another good time for a break. Just have a refill coffees, and then perhaps at 4:55 we regroup here and then start with the knowledge elicitation exercise. All right. Okay. Now we're back in BayesiaLab, and we have a blank canvas. Onto this canvas, we'll now enter the nodes that we think are relevant in this problem domain. We can establish relationships here. And just to help us get started, I will introduce one particular node that will be important, and that is the node that represents the powertrain. So I'm creating a node here, and I'll zoom in. And that first node I call powertrain. And this node I will give 2 states. One state is electric, and the second state is gasoline. Again, making this very naive distinction between the powertrain technologies. So, and I'm using this here because as we build our model, we will now introduce additional variables, additional nodes that relate to powertrain and to the environment. So as we build this model, as we add nodes and relationships, and once we parameterize them, once we elicit our knowledge and enter it into it, we can then simulate what happens if I set the powertrain mix to different levels. We could then simulate what happens if we have 50% electric vehicles versus 75 versus 25, and then see how that cascades through our network, what it does to the overall cost, what it does to meeting our constraints, such as could we have 100% electric vehicles? Would people get where they want to go if all vehicles were electric? Would the constraint be met or not? This is what we want to answer through the network. in general, I think for building this model, it helps to think about, what does the day in the life of an American look like? How far do we drive? Where do we go? All these things. I think it's easiest from creating for brainstorming purposes to think of it as a day of a traveler, a day of a driver.
So are we building a persona then?
Excuse me?
Are we building a persona?
We don't need to build a persona. We rather need to come up with distributions that describe, well, what is the probability that somebody drives over 500 miles? What is the probability that somebody is driving just in the city? And things like that. So, what variables do we need? Who's offering the first node? Yes.
Cost of the vehicle.
Cost of the vehicle. So I'll call that, let's say, vehicle price. And I would argue that that is, at least currently, a function of the powertrain. Agreed? Right now, a vehicle with an electric powertrain, equivalent size car, is significantly more expensive. So I am introducing an arc between powertrain and vehicle price. Now, as we go forward, you will have to assess, well, what is that relationship going to look like in 2025? Perhaps that premium disappears, and then there would be no distinction between the prices. Yes, Ricardo.
So, when we work with UML, we get in the habit of the arrows having a certain way of being spoken. So that arrow tells me the powertrain, the vehicle price depends on the powertrain. So I could read that arrow that way. Now, does that reading have to stay consistent?
Yes, that is important here. So here I'm saying, in a way, the powertrain causes the price. Because right now an electric powertrain, including the battery, is more expensive.
Right.
Yeah.
So this has gone beyond the association, there's actual causality.
Here we are entering our causal assumptions. We're saying it's
affecting, or it's not temporal, but it's
no. Here it is causal. I'm
it is.
but how strong that will be in the future, I don't know. You perhaps will conclude actually gasoline and electric powertrains will be on parity in 2025. But right now I'm saying the price is a function of the powertrain,
Right.
because the other way it doesn't work. Like if you get a discount on your car through haggling with your dealer, that does not change the price.
But
This is not actually causal relationship.
No,
it
This
is.
is price, vehicle price, given powertrain. So as you use
But that's
powertrain as explanatory.
but that's the
variable,
nature of
not
US.
necessarily
Here it is actually causal, because
But
the
the
powertrain, the technology, the difference in technology.
The point I was trying to draw out wasn't really what that arrow was or what we call it. We can call it causal, non-causal, whatever. My point is, during our brainstorming, during our analysis, that relationship, whatever we call powertrain to vehicle price, has to remain the same throughout our network. So we can't say, examples, it's can't be, but now we have to find, okay, vehicle price affects something, 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 something. Powertrain is affected by something, something, something.
Yeah,
That's the kind
those
of
are the things we
language.
will now all put in. I think once we add more variables, I think it will become very
I
clear.
can't say powertrain is red, or powertrain is, I'm trying to draw.
There are other things that are associated with it. Let me throw out another one. I would say energy capacity, just to illustrate that point.
Right.
Let me
Should
introduce.
that be kilowatts per weight?
You could all, well, let me, we could do that.
We can break it up that way, but,
Uh,
so,
Because energy is kilowatts per weight is going to be pretty exact. Energy capacity, kind of iffy.
Well, we can do it multiple ways. Right now, I would argue there is a big dependence of energy capacity as a function of powertrain.
and this is.
Let me just hold on 1 second. So, because at least right now, vehicles with a gasoline powertrain have a way greater energy capacity than vehicles with an electric powertrain. Now, in the future, depending on what battery technology does, that may be very, very different.
And you may not even have battery technology, you may be switching to capacitors on the nanoscale.
Absolutely,
using
could be.
graphite technology,
Absolutely.
graphene technology.
Those are the things then. We can now introduce also a variable that represents mass.
How would you
But-
connect the arrow to
Well, just
powertrain
hold
to
on 1
energy?
second. So we could introduce mass and then say and relate energy capacity to mass. Right now, more energy, I forgot what it was, like 1 kilowatt hour is perhaps 50 pounds or something, no? If we switch to nanoscale capacitors, that may go to next to nothing.
But switching it to kilowatts per weight takes in different technology. as
Even
opposed to
that, right
batteries
now,
or
we can
capacitors.
take into account different technologies because you will be assessing what is the energy capacity in 2025. Yeah, that we don't know. I don't know. We have to use our assumptions here. So let me now introduce that arc. I'm saying powertrain causes energy capacity because right now these capacities are very, very different. Brian.
About energy cost.
Energy cost, absolutely. That's a very important one.
What charging time?
Hold on 1 second. I'll just call this now energy price because later on we'll have total cost. And I'm arguing here, energy price is also a function of powertrain because we know gas prices are different than electricity prices. Now,
Well,
you have to
add
project.
one more factor there because you have the biggest part of energy cost is taxes, and you can very likely by that time period go to taxes per mile, which is going to change your equation.
Absolutely. And really, here we don't determine what that is. Through your assessment comes in your judgment on what that future relationship will be. You may believe that through government policy, these prices will be equalized, or electricity will become more expensive due to renewable energy sources and things like that. So that assessment has to come from you. Ricardo.
Yeah, so this is where I'm having trouble with and this is on the interpretation, like the software obviously is doing what the software does. But here we have, for example, powertrain has an energy capacity. Okay, that's that arrow, that's clear. But then if I apply the same thing, a powertrain has a vehicle price, I semantically, syntactically kind of fail, so I have to say powertrain affects the vehicle price. Now I'm cool.
Yeah.
But now I use that on the energy, powertrain affects energy capacity. Okay, I can maybe meld it, but now powertrain affects energy price. Again, my model fails. So what I was driving at with my initial question is, wouldn't the uniformity of the interpretation of my arrows in the knowledge domain be a prerequisite? So if I'm working with powertrain having things like energy capacity and all that affecting the model, aren't those different arrows than the powertrain affecting the vehicle price?
No,
Okay.
it's entirely consistent because I'm merely saying conditional on the type of powertrain, I have different vehicle prices. Or I could have different vehicle prices. Right now they are, in the future, maybe not. That's up to you. Given the powertrain, we have different energy capacity, but the arc has to go in that direction. It couldn't go the other direction.
And again, on those fundamentals, on the atoms, on the atomistic view of this, I have absolutely no problem. It's when you mix two atoms, in my mind, maybe incorrectly, the atom of some system having a component, compartmentalized, like this is part of the components, versus the system affecting some variable either inside or outside of it. To me, those are two very different analysis. And again, maybe they are
modeling the same, but.
I would say bear with us as
Fair
we
enough.
proceed, because I think once we'll add a few more, you will see the pattern where this is going.
What I want to say is, development of a model to a large extent is subjective. Okay?
Absolutely.
Okay? If you feel that this is not the way to do it, you do it your own way.
All I'm trying out is that I'm 100% with the subjectivity,
Yeah.
but you can't
Okay.
be subjective within.
I'll stop the discussion. We need to keep moving. We need to keep moving. And we will, as we build this model, we will include things, we'll omit things,
Sure.
and there will perhaps things where we're not perfectly happy with it. But I want to get somewhere today, so I'll move on.
You can only do so much in a half hour.
We can only do so much in a half an hour, and I think you will see in half an hour we can get to something useful that is not final, but really gets us off to a good start. So, what else? Weight. So I'll call that more technically correct mass, and very much a function of, again, powertrain, I would say.
Battery life.
Battery life.
Or battery technology.
Excuse me?
Battery technology.
Battery technology.
Yeah.
So what aspect do you want to capture there?
Storage, unit
Energy
price.
capacity.
Okay. So, and
Well, the life of the battery is going to be directly related to the vehicle price in the long term or the maintenance costs.
okay. Or oops, storage cost.
So does something like maintenance costs come under the vehicle price then?
I think that's probably a separate one, because
The selection.
yeah, because here it argue that some maintenance is less expensive on electric vehicles because they probably don't need oil change and certain things, whereas that you have maybe a limited lifespan for the battery. So there are perhaps two variables. One is sort of maintenance cost, and the other one is sort of overall longevity, or vehicle lifespan.
Could it be something vague as lifestyle choice? As vague as that?
It could be, absolutely, because I think
It's green.
green, absolutely. I think this is like
Occupation.
personal
different jobs.
preferences.
Specific to
yeah.
green versus non.
Yeah, we could do, and I will some of those things I will dismiss because they will take us too far.
Okay.
Yes.
Yes, so just to be clear, what we are trying to do now is try to predict how the market share gonna be for electric vehicle.
Mm-hmm. Yes.
And I can be just thinking as me as a consumer whether I am gonna be buying that vehicle or not. Okay.
Yeah.
Okay.
What would you consider? What would be critical for you?
Availability of public transportation.
Ah, okay, very good. Public transportation.
What about the recharge time?
Recharge. Yeah. And here I would
I look at the powertrain because it's really.
absolutely because
How long it
we
takes to put gas in versus how long it takes to charge the battery.
absolutely. So I'll call that energy loading time. So to distinguish between, because there's also time it takes to fill your gas tank. It's just really short in minutes as opposed to hours for a battery.
Now, if you put public transportation, you'd probably throw Uber and the driverless car up there too.
Absolutely. Let's do what we call it, like ride share
Yeah, ride share,
services, and
then the driverless.
sort of driverless.
Who knows who will dominate the market value then?
So now for these three things, because here we're going into somewhat a different area, what do they relate to?
Alternatives.
Do we?
Alternatives.
They are alternatives. but they have one, I would argue they have one common effect.
No driver.
No driver?
No car.
They could impact demand.
That's it. That's what I'm looking for, because that, I think, is really, actually, let me call that the individual vehicle travel demand. And I would say all these three things will very much impact that, right? Yeah? So what else goes in there? Or how else would the vehicle travel demand differ?
Well, you're gonna have things like your insurance costs, which can impact, whether you're gonna be using those services or own your own vehicle.
Yeah, so we could, but there's some more fundamental things. Let me steer this to a more fundamental debate. I was doing this seminar in New York City. Then I did it in Southfield, Michigan. I think people there will differ very much in how far they drive, right? So I would argue that the environment in which you live has a huge impact on your travel demand. So in what ways should we classify environment?
Are you talking
Sorry?
population density?
Population density. Here, perhaps I will argue, we could split it into rural, suburban, and then urban. So for this variable, for the others, we haven't really established any states. For powertrain we did, but for none of the others. Here for environment, I'm now saying 3 states: rural, suburban, urban. Yeah?
How likely that vehicle will be stolen, for example?
Where do you live?
Something like that.
So here I could also say the environment affects public transportation, and environment affects individual vehicle travel demand, absolutely right share services. In some parts of the country, Uber doesn't exist. But then driverless technology, I think, is probably not affected by environment. Because you could have
Let me
driverless.
ask a question about that triangle you set up.
Uh-huh.
So environment to individual vehicle triangle, that arc is just saying, just the environment?
It's saying that
Just the environment, that arc, just that one?
yeah.
And then the other one, the one that goes through public transportation, is now saying, starting with the environment and taking public transportation into account, how does that affect everything? And so then the final machine will take both of those paths.
Yeah. So here we have a direct effect, if you
Yes.
will, and an indirect effect via a mediator.
And then the final result is a combination of both of those.
Exactly. Yeah.
Right.
So this is what we're now doing, and now very quickly we'll get to the point that this node will have very many parents, which will make it very difficult to elicit. So we'll probably have to trim down and focus on perhaps the more important ones first.
Now, do we have to focus on the job of transportation? Like, right now, everybody's going to grocery delivery and such, which eliminates a number of vehicle trips. So as the technology advances, do we have to figure that in at all?
I would, yeah, I think
Okay.
totally. So
And
here we
where
could
would
say travel purpose.
Now, can you do with this one what you did with the environment and put some states in?
Yeah, we could. So we could now have a distribution, or I'm just throwing out some states like commute, going to school, shopping.
Exactly.
And
'cause I know
states like that.
When they'd done that, there were certain states people traveled.
Yeah, yeah, and that travel purpose probably also depends on the environment. If you live in Midtown Manhattan, then going shopping is probably not a travel purpose you have.
And if you're out in the rural areas, you may do like a weekly because you have to go much farther to get to where you can pick up stuff.
Absolutely, yes. So now, two things are emerging here. This is describing the powertrain characteristics. This is describing kind of the environment and the user, the driver. So now we need to think about how that kind of comes together. And I think there's an obvious one. I think we're missing one important variable here. And I think that is energy efficiency we haven't talked about. Because as we saw earlier, right now, there is a huge difference in energy efficiency between gasoline-powered and electric vehicles.
It's something like a miles per gallon.
Miles per gallon, or as we refer to it now, the kilowatt hours per 100 kilometers. So.
And we're not talking, at this point, we've already limited it out, the hybrid, like using a hydrogen and a electric cell.
Those we're just ignoring. Yeah. Obviously, powertrain could have like 10 states. Right. I think diesel powertrains are really the technology to go. That, I think, would be by far the best technology, but now that seems to be, like, for political reasons, out. But anyway, so we could look at many different ones, but here just gasoline versus electric. So
by the very nature at this point, we've defined some things are in scope and some things are out of scope.
Yes, and really omitting these different technologies is just like for simplicity. Yeah. So let me now, one thing that we haven't included here yet is, and something that is very important, what are we all anxious about with electric vehicles?
Safety.
Oh, really, safety?
Getting stuck.
Why?
Number of refill stations.
And that is related to? Recharging? Range. Nobody's talking about range anxiety. That's the one thing.
And yet energy capacity, isn't that right?
Energy capacity we have, but that translates into something.
Well, we also missed another big one on demand, which is the ability to purchase.
In what way?
Market.
No, it's just, if you look at the different markets, there's, you're gonna have some people who can afford your Rolls Royce and a lot of people who aren't gonna be able to afford the Rolls Royce. So depending where these things fall and how the economy goes, you won't know if someone can buy this market segment or not buy this market segment.
Yeah. Here I would argue that if there is a market, car makers will build what is wanted.
Okay, so this would be something we would put out there.
I would agree. I would say let's remove that. Car makers are very good about figuring out to build the cars that people want.
So we're going to assume that they will build what the market demands.
Yeah. Yeah. Now that could be prevented by government intervention and through regulation and so on. But by naturally,
at this time, this is an assumption we're making.
Yeah, that's an assumption I would like to make, and I hope it's not too unreasonable.
Now, do you ever keep track of your assumptions?
Well, here, this is what we're in a way doing by spelling out what we include.
Okay, so this shows us our assumptions. And
This shows, yeah.
We're not gonna make the deal make this perfect. We're just trying to learn the tool at this point.
Yeah.
Exactly. So here is something I want to do. Range, and I'm arguing that range is a function of energy capacity and energy efficiency. So now, here that's an easy node to include because that is just a deterministic function. That is not something where I need your expertise, because this is just merely, this is my energy storage, this is how much I need to travel a certain distance. That gives me my range. Yeah? And this is where now things become interesting, because I can now introduce a constraint node that now compares what is the capability of the vehicles versus what is my travel demand. I can see if I had 100% electric vehicles, with our assumptions about their capacity and efficiency, could they really do what we want them to do? You know, given the assumptions that we make about how people want to travel, where they want to go.
Stefan, I have a question. So this is a fascinating discussion, but it is, you think it is making a difference that you know the subject or that you know the software, or both? To accelerate this, which person would you prefer to have driving this if you were to mimic this in a different form?
Well, that's a very good question. Now, there is some expertise that's kind of needed about the concept of Bayesian networks. I think the most important thing is that you have an unbiased facilitator. You know, I'm not necessarily an unbiased facilitator. I know exactly. I think I know exactly where this should be going. So I would perhaps not be the perfect one to assist here in an unbiased way. And in practice, you can't always have an expert in every single field. So inevitably, when you run these workshops, you will have facilitators that are not familiar with the subject matter. I chose this topic because I felt like I have some familiarity with it. But it's a very fair point. I think the most important one for a real-world knowledge elicitation session, you want to have a very unbiased facilitator who really takes the guidance from the group.
Another question. The reason that why you put constraint there is because you are kind of smelling that is a phenomenal dependent variable for the whole thing? Or
well, no, I'm because the way we want to model this is we want to have a set of variables that characterize the powertrain, and then we have a set of variables that represent the travel
needs.
demand, the needs, and then we need to figure out how can technology meet the demands, and more importantly, how can, and let's put this together, which mix of technology can meet our needs at the best cost, at the lowest cost. Because I think that's what will determine the natural demand for electric vehicles. Yes, Ricardo.
So if I want to read the notes, could I read it this way? Energy capacity versus energy efficiency will give me a sense of the range, and then the range versus the individual vehicle travel demand will give me a sense of the constraint, whatever it is. I mean, is that a...
I wouldn't say versus.
That's what I'm trying to drive. Like, there's this versus sense that I'm...
And I think that's misplaced.
Yeah.
Yeah? Here you need to... This is not... This is not a decision tree. This is how we think the underlying world, how the domain works. What I'm introducing right now here is, I'm saying the total cost is a function of energy efficiency, energy price, and how much I travel.
So that's right. So if I have energy capacity and energy efficiency, if I draw both of those as a graph, wouldn't I be able to get the range from that graph? And that sense, I'm not saying that's what's being done, just to get a sense of, like a baseline sense of how this is being, how I can speak this.
Well,
right?
what you're referring to is, here this is in fact a deterministic function, because energy capacity and energy efficiency are just...
On a graph. Like if I give you
you could represent that as a graph. It's just a deterministic function
right.
here. So that we don't need to elicit. And so,
it's just that it's not that it's hard seeing, but I'm really seeing that as like, if I have energy capacity, energy efficiency, I can think of that as a graph. Now you put a third arrow in there, like with individual vehicles, that to me reads like a four-dimensional graph where there's 4 dimensions going into that decision.
Yes, but that's not a decision, that's
Or, I'm
rather,
sorry, the result, the outcome.
yes.
The outcome.
So, yes,
It's a
that is,
four-dimensional-
this is a four-dimensional table, in fact.
That's
Yes.
what I'm saying.
And that we will need to elicit from you, because you will need to assess, given the availability of public transportation, given driverless
Right.
technology, given that you live in an urban environment, and so on, what is your travel demand?
Right.
So
now you
let's,
have-
sorry, we need to keep
Yes.
moving. Yeah, we need to keep moving. Sorry, all good questions. So let me now connect all this here. And this is approximately how I would like to see this. So here we have all the attributes of the electric vehicle.
What about your orphan nodes?
Let me get back to those later. Yeah? And we will not include some of these nodes simply because we don't have time to elicit all of them. But we would, for instance, deal with energy loading time in a very similar way. We would look at energy capacity and range because, you know, if it takes 24 hours to load a battery in your garage, you know, then you really don't have time to drive the car because you need the entire time to charge it. So you could then create a constraint. What is your percentage of vehicle usage versus vehicle parking time? And then is it enough time to charge it? And will you be at the right place, have the right amount of time, and have the infrastructure to charge it? We'll leave this out for the moment. But this would follow the same structure that we have here. So energy capacity, energy efficiency affect range. We have an individual vehicle travel demand that must be met. So as we try out different levels of powertrains or different mix, we will see whether our travel demand can be met. Furthermore, travel demand and energy price and energy efficiency affect total cost, the travel cost. Now there are other costs like maintenance cost and vehicle price that could be baked into this, but we'll leave this out for now. So for now we're just saying, what's the cheapest way to meet our travel needs? Can a certain powertrain mix meet our travel needs, and how much would that cost? Yeah?
Given the constraint.
Given a constraint, yeah.
Because here, right now, you know, unless you explicitly know the constraint and the total cost, otherwise the information from individual vehicle travel demand cannot propagate it to the
Yeah.
data side.
So I'm going to show you how I'm ultimately specifying this. I'm just conceptually illustrating this here. So we want to find a solution that gets us where we want to go, and we want to figure out which solution is the least costly one, because I think that's what consumers will choose. The cheapest way to get them where they want to go. That's the assumption here. And that is now what we have structurally represented here. Here's what determines our demand. Here is what the powertrain characteristics are like. These interact here in these nodes through the constraint and through the cost. So now we have the basis for knowledge elicitation. Yes, please.
So for your constraint, if you were put states, would that be yes, no, or maybe?
Could be true,
okay?
false, yes.
Okay.
Yeah.
And for this exercise, do you also give percentage of yes constraint, no constraint, or don't even care?
So here in this case, it will be deterministic. It will be a comparison of range versus travel demand. We will see, what's the distribution of our ranges, our available ranges, and then what's the distribution of our travel demand? Does that meet it, or is there a shortfall? If there's a shortfall, then we nix that solution because that doesn't work.
Deterministic, 0 or 1, there's
Yeah.
no probability there.
Yes.
Okay.
Yeah. So and now there are a number of other variables that I will propose, because now you can imagine this would now take quite a while to go through all these variables and elicit the probabilities and get your assessments. We have 25 minutes left, so what I will now do is switch to a prepared model, a highly simplified model that I think will still capture the essence of what we just discussed. Hold on, let me go to the appropriate slide. Here we go. So this was my initial vision of how the models should be structured. This is how I practically implemented it. So up here, we have a number of external conditions. Environment, this is what we had in our model. Now, we did have the variable travel demand as a function of the environment. What we didn't have is the type of driving that we would do in each environment. I'm arguing that depending on where you live, your city and highway driving is different. You know, so if you live, again, in Midtown Manhattan, you probably don't do a whole lot of highway driving unless you go out on to Long Island on the weekend or go up the West Side Highway or something. So your highway driving may be quite limited. If you live in Idaho, you probably do lots of highway driving. Another thing we didn't include is vehicle type, because depending on where you live, you may be more likely or less likely to drive a pickup truck or an SUV. You know? So there's probably a different type of vehicle mix as a function of where you live. So another variable that's here that we also identified is energy cost, which is different depending on powertrain. Now here are the variables that reflect the powertrain, energy capacity, energy efficiency. Here at the bottom, these are our constraint variables. It's just slightly differently specified than just with a simple constraint node. But I'm not going into the technicalities of these nodes. Essentially what I've done, I've created a simple penalty function that if the range doesn't meet the travel demand, it creates a penalty on the overall cost. So I've baked everything into a total cost variable. So it is essentially searching for solutions for the least expensive feasible solution. That's the objective here. Okay.
But in order to get this network model, you must have had all these parental distributions information, all the condition distribution information.
No, here we don't have anything. This is a blank network. So now the next step is, it's your turn. Now we will go through this. That part, we now need to elicit from you. This part, this is merely deterministic. It just compares, is the travel demand within range? How much does it cost? So we need nothing here. We'll just need to elicit these there. And even there, we'll do a little bit of a subset simply because we don't have much time left. Just to give you a sense of where the endpoint is, once we have elicited all these probabilities, then we can say what mix of powertrains basically minimizes our cost within the constraints. And we're saying that's probably what the natural demand is. No? So, okay, let's now focus on this part here and start to elicit. The first elicitation is about environment. And this is what I will post to you momentarily. We have 3 states, urban, suburban, rural. And I just have a uniform distribution here as a placeholder, but that will be blank, and you will have to set your own expectation or your own beliefs here. Then the second one will be the mix of vehicle types as a function of environment. Then the type of driving as a function of the environment. And then the fourth one will be about the distribution of driving distances as a function of environment. Now, given the limited time, I suggest we'll just do this one, and that one. So you'll see how this works, and then for all the others, we'll take the default values that I had previously just put in there. Yeah? So we're now at this point where I will take that model, post it to our server, and then you will be able to provide your assessments. So take out your laptops, please, and sign into this website, or rather, let me go around the room first and assign you your user numbers. Okay, I'll just perhaps start with James. You're number 2, number 3, number 4. Anyway, just
I'll share.
okay. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, Brian 14, John 15, and 16. Do we have you, James? No.
Yeah, you do. I was 3, but I don't have a PC with me or a phone that has web access.
Okay.
So I'm immaterial.
Okay. So everybody has a number now. Good. So that's important. So remember that number. And I will show you now how to use this number. Your username now consists of B key, then followed by the number that you were just assigned at Bayesian.us. This is your username, and everybody has the same password, BayesiaLab 6. Yeah? So once you get to this website, click on Sign In with Bayesian, use the username and this password. Does it make sense?
Are you going to be user 1?
I'm user 1, yes. Yeah? Okay, so once you're logged in, you should get this screen. And I would like you to select, simply click on Session EV.
You come back one.
Yep.
Okay.
So once you have selected EV, you should see something like this, waiting for an assessment to be posted by BayesiaLab. Yeah, everybody there? Yeah? So just let me now show you what I'm going to do. I will now host this assessment task. Actually, let me show you this. From within BayesiaLab, from my network, I will host the assessment task, which will then show up in your window. So you will be able to say, well, this is the distribution of drivers between urban, suburban, rural. Yeah? So I will now post that assessment task. So I'm now in Bayesian. Are you okay?
We're going to the powertrain.
To me?
You got a different page.
You double clicked on it, you got to the powertrain, maybe we should have done that.
Sorry.
Go to the powertrain.
You double clicked on it, it ended up in some kind of powertrain thing too.
Reading powertrain.
You don't know how to get back.
Oh, this is perhaps, this could be that's a leftover from yesterday's task. Hold on, let me just check that. Yes, sorry. Here we go. This was a leftover task from yesterday. Yes, that's so. I will close out of that, go back, or click validate, or go back.
So it's just the back arrow?
You can.
Click and choose two items back from the back arrow. Don't go back, you won't even go back. Drop down and choose the main sign-in one again. Click and hold on it, and then choose like two back.
Just perhaps go back to the login page.
Okay.
Yeah, just go back here, and then you should be taken automatically to. Yeah. Okay. So.
Okay.
So, I will now post the assessment task from my screen. So, is it popping up for you?
Yes. What's it supposed to say?
You're now supposed to see this. You should see three sliders that give you, that show urban, suburban, rural, where you can now set the distribution as per your beliefs. Furthermore, I should point out there's also a slider that is called confidence, through which you can enter your subjective belief as to how confident you are in your assessment. Yeah?
You can change the numbers.
You can change the numbers. You're entering what you think, what the distribution is. Now, the other week I had somebody from the U.S. Census Bureau, and he said, you know what, this we don't need to estimate because we have data on that. Of course. And this may be a situation where in some of these nodes you have data, on others you don't.
Is this a total population, or is this what we expect the people that are buying their electric vehicles to be?
Yes, vehicle buyers.
Electric vehicle buyers?
No, vehicle buyers.
buyers.
Yeah, or think of it as the population of drivers. Yeah. In 2025, yes, in 2025.
What are the check boxes for?
You can fix individual values because these are the sliders are linked.
Have to be sum up to one.
Yes.
The one technical thing on the confidence, is that like a weight when you
This will be used as a weight. Yeah.
weight on an expert on this individual data point?
Yes. And I can see how you've rated yourself, and as the facilitator, I can also override your own rating.
Then we validate.
Sweet. Then you click validate. That's correct. Yeah. So.
Are the comments usually used also?
Yeah, that is often helpful because sometimes, like what was just said about, is it drivers, is it population? You may put down like, I was referring to drivers, I was referring to new vehicle buyers, and then we may realize there's actually a misunderstanding. And then we can correct that and then say, okay, now that we've clarified this, let's rerun this as elicitation. So, now this is what you would normally not see because we said this is all anonymous. So this was what only I would see. I now see who has responded, and I can see how you've responded. Yeah? So here I have all you experts, how you responded, and what confidence you assigned to yourself. You know? And I can now use this to establish how far people agree or disagree. So I can see user 12 thinks only 2% of drivers are in rural environments. You know, somebody else thinks it's 24%. So this may now be something where we should perhaps have a discussion, not necessarily like, hey, you know, look at him, he said 2%, ha ha ha, you know, but rather like, okay, let's talk about the conditions again. We're talking about drivers, we're talking about new vehicle buyers, and so on. And so therefore we may reiterate this question once we've clarified the issue.
So this is blind, not double blind. You still know who's.
I know who's.
Just we don't.
You don't.
But you're gonna pretend when you're the facilitator that it's blind.
Yes.
And the time is how long it took them to fill it out, is that used as the compensation?
No, it's just for reference. Yeah. Now you can see how this can take a significant amount of time to go through these steps when we do this interactively, because we always have to wait for the last one. So in practice, what we do most often is we go through a few steps together as a group and then assign the rest as homework. So then you would process these questions offline instead of.
So you can actually have I'll call it a bank of validations that we have to go through.
Exactly. We call it a batch process. So that you can then work on offline, and then we'll say by tomorrow morning we'll have everybody submit their results, and then I will automatically have that here, and then we can share the summary of the results, and then perhaps address some issues. Sometimes it's often just a misunderstanding. Well, what is up, what is down, which way does the scale go, and so on.
And this may drill too deep, but do you have any kind of control versioning system so that the response is if we ask the same question, I mean, something like that, or is it basically just one model at one time?
Well, here it is one model at one time, but you can.
Sure,
That's what I do in practice is I do iterations of that file, so I can also compare the progress.
Right. And there's never going to be an iteration that you as the facilitator aren't offering or aware of. So it can't be like I'm a user and I log in at 2 o'clock in the morning to quote unquote change my answer. Would that then be how, like how?
But you here in this case, it's not like you're being locked in. The whole purpose of this is that through iterations, through question and answer, we all better understand. So if you think, you know what, I changed my opinion given all that has been said, I would like to resubmit my answer, and absolutely that is the purpose here.
And for better or worse, that's not stored. There's no record.
There's nothing that will penalize you for having changed your mind. Okay, we've got to keep going.
Just record.
Yeah, but let's move on from that issue. We've got to keep moving. So next elicitation task is about the mix of vehicles between the different environments. So I'll post that task again. And now you will see you will actually go through 3 screens. The first one is you will look at the distribution of vehicles in urban environments, then suburban, and then finally rural environments.
So do you normally time box all your iterations? So if someone doesn't make the time box, you just ignore it?
Well, as I said before, for the first few ones, we would probably do that all together. But then given that somebody may really want to think about it, it's better then to have the bulk of the question dealt with offline. Because this is not an exam. This is really, we want you to think. Yeah, we want you to think about what do you truly believe based on everything that you've heard. So to cut you off because you don't respond within a time frame would be kind of against the philosophy of this approach.
Because we use so many conditions.
Yeah, but I mean, to do the next iteration, don't you have to,
I mean, if you're just not responding and not participating, then we'd say, okay, we've got to move on, and I'll just close that question, and then we would not take yours into account. But that's not really what we want to do. And in the batch mode, you may not do your homework in time. Inevitably, then you're out. But obviously, the whole purpose of this is to get all experts to contribute.
but not all SMEs are very responsive sometimes.
Yeah, that's the real world. And there's also a challenge of this because, as you can see, there could be very many assessment tasks that result out of this. So if I give you 1,000 assessment tasks as homework, you may go through the first 10 and then just give up. So there are then all the issues that are related to, questionnaire fatigue that we have with surveys and so on. So.
Do you ever ask or try to find out how much time people are going to have available to participate as your?
Obviously, we would want to, we set expectations, and when we set up these workshops commercially, then we say, this is going to take 3 days. This is not a quick, one afternoon thing. You need to be here for 3 days, and you will have homework. To set very, very clear expectations that this is serious effort, and that often limits the size of the group. Yeah.
So this is like a classic Delphi method right now.
Yes,
Yeah.
the asking of the questions,
Yeah.
submitting the answers, and then playing back the results to you, that is classical Delphi.
So you're going to show the results on the screen to us
Yes.
and ask us if we want to revise our decision.
So for instance here, this is now, I'll just make this a little bit larger so you can see it. Hold on, why is this not working? So I'm just showing you very quickly the table that represents the summary of what all of you said. Excuse me?
Is that the averages of our responses?
This is the weighted average of your responses. But I see this little icon here that tells me here, this is not very visible because of the projector, but this shows me to what extent you're in agreement or disagreement. So depending on how strong that is, I may say, we need to discuss this. We need to bring up this issue again. And you know what? I may be thinking about Germany. Alexeyev may be thinking about the Ukraine. So it's like, okay, well, we need to introduce country as a variable. And then reassess that with the respective country context. Huh?
Sounds like we're in a scrum meeting.
Do you ever go back and change the model based on these questions?
Oh, of course,
Okay.
because then you realize, that we didn't.
Anticipate
The country needs to be in there. Yeah, yeah, absolutely. So we're almost out of time. So we'll conclude it here at these 2 assessments. But I think you get the sense of how this works. And obviously we have many more here: travel demand, energy efficiency, energy cost. Yes, please.
I have a quick question.
Mhm.
So you kind of assign a name for certain regions in your model, right? So sort of cluster of ideas, which is analogous as you do the Bayesian clustering to create sort of factors, right? With the problem. So is there a way to actually create factors or a new node that represent the knowledge of all?
Absolutely, you could do that, because now we're, and actually that's a whole new topic that we could talk about, clustering, factor elicitation, or factor induction with Bayesian networks. Now, there are 2 things to say about it. If we had data, we could use machine learning. We could use machine learning for inducing factors. finding latent variables.
In the absence of data?
In the absence of data, what we can do here is we can take your ratings as data and then learn clusters from your answers. So we can then see like how the participants cluster together. And what we very often see is that people from a similar business background or from a similar region, or even people who sit together, kind of answer in a similar way. So that's a very interesting analysis because we can then discover schools of thought within the experts. And we may see, you know, there are really two different ways these people think about it, which is then an interesting debate in itself. You know, they have like the people who sit on the left side of the room answer systematically different from the people who sit on the right side. And then that's the question. And then perhaps we are missing something. There's perhaps a context variable that we have not included that is kind of a hidden cause of your answering behavior. Yes, please.
So the context variable, like what we just did with the vehicle type, is given whether it's urban, suburban. That's always the parent node. Is it? Okay. So like for example, if we're looking at the energy efficient, it has 3 parents. So when we get to there, it's going to be a combination of all 3 parents.
That's correct, yeah. And you can see how the complexity can quickly explode for these. And so in the discussion, we need to early on figure out how many states can we afford to have, because you know this becomes a hypercube, and we would have to elicit all these probabilities. So,
is there a technical maximum for the software for the number of parts?
No, that is not. So that could be enormously large.
Float large.
Yeah. So, okay, let me just now fast forward and switch to the model I had previously created, but now just with default probabilities. Now, I just want to give you a sense of how it works conceptually. So here I just have all default values. Unfortunately, we don't have time to now take all your actual assessments. And this is now just the same like the network the doctor produced. Like the network we learned from data, this network was produced by you, with your assessments. And now we can use this to figure out, well, what powertrain mix would on average give us the least amount of cost with the max while meeting our constraints. So the way we can deal with this or do this is using an optimization in BayesiaLab. So I can now select my powertrain, my variable. By default, I just have it here as 50-50. And I can now ask BayesiaLab to try out different powertrain mixes to see what meets the constraint and what minimizes our cost. So, and perhaps, just to make this a little bit more interesting, I start with conditions that are perhaps very favorable to electric vehicles. Let's perhaps look at the subset of, purely city driving in urban environments. Because I have a hunch that that's the best possible environment for electric vehicles, where a sizable chunk, where we should really end up with a sizable mix of electric vehicles. So let me now run this optimization under these very specific conditions. Analysis, target optimization, and here I'm using a genetic algorithm, even though in this particular case it's kind of overkill, because we're just trying out a single variable. This target optimization algorithm typically you apply perhaps on dozens of variables. So target optimization, I'm now searching across different levels of powertrains, and here comes my result. The best solution that we found is in this environment, urban city driving for cars, the lowest cost we would achieve with a 46% electric powertrain mix. So that's for that environment. Now we may wish to optimize at the national level without.
Can you give me any, like, uncertainty estimates or anything like around on that?
Yes. Well, here in this case, the probability, that is our uncertainty. Because in a Bayesian network, everything is dealt with as a distribution. So you don't have an uncertainty on top of the distribution. Know what I mean?
So I didn't see the screen, was that just a point estimate or did it give you a distribution?
So in this case,
Looks like
you
there's a range.
you get, let me just show you this. This is the distribution, which in this case of a binary variable is equivalent to a point estimate. Yeah. So, but this is the probability distribution. So let's remove that again and now do this at the national level. Just a guess of what you think will be what we're going to get for the national level. I know you've submitted your response earlier.
49.5.
49.5.
Less, because, well, more the nation's coal than electric, so I'm gonna go less than.
Okay. The group yesterday was very good. They were almost perfectly spot on. So let me run this again. A big fat 0%. And that is really a function of a problem of the constraint, because when we look at the real world distribution of driving patterns, almost anybody, at least some of the time, has travel distance that exceeds the range of an electric vehicle currently. So without behavioral modification, an electric vehicle can't be your exclusive form of transportation.
But that's also assuming you don't have two-car families.
Exactly. So that is what we haven't included here at all.
We didn't include any recharging either.
We didn't include any recharging. That's correct. So we could include the number of vehicles that we have in a household, and for instance, for the Nissan Leaf, it's very typical. It's like a second or more likely even a third car in the household. So this would be a model that only applies to one vehicle per driver, and under the distribution of travel distances, it can pretty much not meet the demand right now.
Would it be a fair rule of thumb that if I get an optimization and I get like a 0 or 100%, that probably I'm either over or under, like there's something else going on, or just as a rule of thumb, obviously?
Not necessarily.
Okay.
Because here it would be very quickly to figure out, well, gee, the reason why that really is because our travel demand has this long, thin tail with a small percentage of long-distance travel.
So it is accurate. I mean, that it is still.
So in
accurate
that
result.
case, it's perfectly plausible. So
Right.
this would now lead to the question, but people have 2 cars or 3 cars, so we would add this
Yeah.
as a variable in a model, or we'd say, it's not just this, but people could recharge after 200 miles.
So the right word is not incorrect. It's just there's something that there's usually something else going on.
So now we see here very clearly it's the constraint. It's not the cost, it's the constraint, the travel demand, the energy capacity. So what we would have to do now is look like, okay, it was unrealistic to consider 1 car per driver. So let's now model multiple cars per household. Let's model the infrastructure and the recharging time. How could that fit in? And then we would get back to the drawing board, implement these new nodes, and then elicit again.
Is this what you mean by going backwards and redoing?
That is, well, there are 2 ways of redoing it. One is merely reassessing what we just went through, but sometimes you will realize, you know what, the 2-car or 3-car household cannot be represented here. So we actually need to go back to the structure. Alexander.
What about validation of this model? Because you can use the same, for example, you can do the same thing with regular linear models, or you can do excess, let's say, this within Dempster-Schaffer model, approach, and what about validation?
Well, validation of this you cannot do until you actually have data, until you get to 2025. That's the first time you can validate this. So that's the unfortunate. There's no test data set, no holdout sample that we could now test this against. This is just merely as good as what we're putting in.
Yeah, but the environmental factors could be changing year by year, and you can adjust that.
Absolutely. So we can now, and it was interesting because when I was at Nissan, that was a real business question. So 7 years ago, before I left Nissan, one of our tasks was to establish, well, what is the potential for the Leaf? Now, of course, now that the car has been in the market for 5 years or so, now data exists. So now there's a way to validate that original model. The original model at the time was overly optimistic. So this model we couldn't validate truly until 2025.
But as we got closer to 2025, can't we narrow?
Yeah, because absolutely we would now say, on this one, we get an update on battery technology. Tesla is now launching Model 3 at this lower price. Range is longer and so on. So we would quite naturally update this, and we would perhaps see the model move in one direction or another. But hard data we don't have at this
But you
point.
still have the basis of a model to work from instead of reinventing the wheel.
Yes. There may be another breakthrough technologies coming out, that we don't even know about, that will throw a complete wrench in the works. So, I think you now have a little bit of a sense of how this works conceptually. I just want to quickly share with you what we could do if had we finished this model. We could now publish it to the BayesiaLab web simulator server, and we could share it with the world. So our colleagues, our stakeholders could now experiment with the model that we set up. They couldn't change the model structure, but they could enter their own assumptions and now say, well, what if the electricity price goes up? What if travel demand goes down? And so on. We could include nice icons, logos to make that perhaps a little bit more user-friendly, and thus allow other folks to work with the model that we designed. So
you're playing a massive what if.
Exactly. And I think that's usually a good way to get buy-in, because if the model that we created is reasonable, then others will say, yes, that reflects the dynamics that I have in my mind. If the model does something completely different, what somebody's expectations are, they will probably tell you and say, hey, this is not how the world works. And of course, the further out the model projects into the future, the more difficult it is to assess it.
Of course, all models are wrong, some are useful.
Yeah, and so what we're trying to get for is get a little bit closer to something useful, other than there is no way of knowing. That's the purpose of this. And I think with this systematically putting together relationships and assumptions, we get to something that helps us better understand the domain. That's the objective. Yeah. So most of this you can now try out yourself. We have two types of trial versions. One is a public trial that is very limited, but we're very happy to offer you a full unrestricted trial that is like equivalent to the full commercial version. You just need to let us know. Just email us and we'll set it up for you. I already talked about the book. The book in chapter 7 has the entire example with the financial machine learning. I think you can easily replicate it, Perhaps you'll find it interesting. There are numerous other examples as well. And as I said earlier, our courses are very popular. People love them. So please consider joining one of them. Also, we have an annual conference where you not only hear from us, but rather from folks who have built models with BayesiaLab, with Bayesian Networks. John and Brian, I think you were at our first conference in Orlando, Florida. They did a great presentation at that time. Last year, we were in Nashville, Tennessee for the conference. The reason I'm also sharing this with you, most of these seminars, all of the talks at our conference we have recorded, so you can go on our website and look up what different people did in different contexts with Bayesian Networks and BayesiaLab. And finally, if you're interested, join us in Paris this year for our 5th annual conference. This will be the first time we're hosting our conference outside of the US, and I think you'll love the conference, and of course the food and the wine and everything that Paris has to offer. So this should be great. Start working on your travel approval now. It may take a while.
And your
So,
passports, yeah.
yeah. So any final questions? No. All right. With that, I'm sorry that we've gone over. I really appreciate your interest, and please stay in touch. Reach out with questions. I'd love to continue the conversation, and have a great weekend.
Thank you.